Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 30 on simple areas.
As we begin Chapter 4 of the course, we're going to turn from our classical tools of Taylor series, limits, derivatives, and integrals, and begin putting them to work. We'll focus on applications of the definite integral, beginning with some simple area formulae. We'll start small, but work our way up to bigger things.
You might think that when computing areas, there are a lot of formulae that you need to memorize. Well, fortunately, that's not the case. There's one formula that you need to know for area, and that is that area is the integral of the area element, dA. What do I mean by that? Let's recall some of the classical area formulae that you learned when you were in school. The area of a rectangle, or a parallelogram, or a triangle, or a circular disk. These you know, but do you know why they're true? They're true because they are the integral of the corresponding area element. Let's see how this works in a few examples. Recall a parallelogram. Now, you would probably argue by rearrangement that if you cut into pieces and reshuffle, then you can build a rectangle, and we all know the area of a rectangle. Well, that's good, but there's another way to think about this. Consider your parallelogram in the xy plane with the base on the x-axis, and then slice it into horizontal strips of, if you will, an infinitesimal thickness, dy. Then what is the width of each strip? It is, let's call it b, the length of the base of the parallelogram. Now, how do we get the area out of this? The area element, the area of this thin strip is, well, b times dy. Thinking of it as a rectangle with one edge of infinitesimal length. The area is the integral of the area element. That is the integral of b dy as y goes from 0 to h, the height of the parallelogram. And now let's see how it falls out. The integral of a constant dy is that constant b times y. Evaluate from 0 to h, and we obtain simply b times h, which we all know is the area. Now, there's a slightly different perspective we can put on this, namely that when we shear that parallelogram and slide the horizontal slices so that it becomes a rectangle, then we are not changing the area element. This shearing preserves the area element, and thus the area. That's a different sort of rearrangement argument, one at the infinitesimal level. This also helps us make sense of the area of a triangle. You're probably used to thinking of it as half the area of the bounding rectangle by using geometry and similar triangles, but we could do things a little bit differently if we also arrange this triangle so that the base is along the x-axis and shear it horizontally so that it becomes a right triangle. We see we have not changed the area since we've preserved the horizontal area elements. Now, the hypotenuse has the equation of y equals h over b times x. Now let's consider a slightly different area element, this one vertical. The height of that vertical strip is going to be, from our equation for y, h over b times x. The thickness is dx. And thus, computing the area as the integral of the area element, what do we get? We get the integral of h over b x dx as x goes from 0 to b. And now, what do we see? Well, h over b is a constant. X integrates to x squared over 2. Evaluating from 0 to b gives hb squared over 2b minus 0. Simplifying, we get 1/2 base times height. Very simple. The example of a circular disk finally takes us to a nonlinear case. The classical means for determining its area was to use an angular variable and to approximate as a limit of triangles. Let us do likewise. This is perhaps not exactly how Archimedes did it, but it's kind of close. Consider an angular variable, theta, and consider a wedge defined by an infinitesimal angle, d theta. Then, thinking of this wedge as approximately a triangle, not exactly, but approximately a triangle, to first order, what would the dimensions be? Well, we would say that the height of the triangle is roughly r, the radius of the circle. The base is going to have length r times d theta. That in mind, the area element is what? It is 1/2 the base times the height, that is r, times r d theta. The area, being the integral of the area element, is the integral of 1/2 r squared d theta, as theta sweeps all the way around from 0 to 2 pi. Now we know what? Well, wait a minute. There's no theta in the integrand. There's just r squared, which is a constant, as is 1/2. So we can pull out the 1/2 r squared. The integral of d theta is, of course, theta. Evaluating that from 0 to 2 pi gives 2 pi times 1/2 r squared. That is pi r squared. The classical answer. Done very simply. But this is not the only way to do this problem. Consider if we used a radial variable and we sweep out thin annuli and fill up the disk in that manner. Let's call that radial variable t. The annular strip is going to have thickness dt, and now we need to argue that the area of this infinitesimal annular strip is the circumference, 2 pi t, times the thickness, dt. I'm not going to argue that that's really correct right now. Let me just state it, and let's see what happens when we integrate it. We get the integral of 2 pi t dt as t goes from 0 to r, the radius. That is, we get pi t squared as t goes from 0 to r. That again yields our answer, which, if nothing else, tells us that our area element was indeed correct. That is a very simple integral. But notice that it's not the only way that we can do it still. We can cut the disk into slices, let's say vertical slices, and we sweep from left to right. Placing the circular disk at the center of the xy plane allows us to use a strip of width dx and height given by what? Well, the equation of the circle is x squared plus y squared equals r squared. Solving for y gives plus or minus square root of r squared minus x squared. The area element, in this case, is going to be the height, that is twice root r squared minus x squared, times the width, dx. Then we see that integrating to get the area gives the integral of twice root r squared minus x squared dx. Evaluating the limits from minus r to r, what do we get? Well, this integral is not as easy as the other two that we've done. It is an even integrand, over a symmetric domain. So we could pull out the 2, double it, and integrate from 0 to r. But we're still not done. We would need to use trigonometric substitution, something of the form x equals r sine u, and do a little bit of work. I'm going to leave it to you to verify that what one gets for that integral is pi r squared over 4, leading to the final answer that we all know and love. Notice that depending on which way you split the domain up into area elements, the resulting integral may be trivial or maybe quite involved. This, then, leads to the example that we all know and love, the area between two curves, let's say f on the top and g on the bottom. Now, it's very clear, given what we've done, how to determine the area element in this case. Using a vertical strip, its height is going to be f of x minus g of x. Its width is dx. And so, integrating this, we see the classical formula that you've no doubt seen before. The area is the integral of f of x minus g of x dx as x goes from a to b. One interesting application of this formula is to economics, in the definition of something called the Gini index. This is a ratio that is used to quantify income inequality in a fixed population. It relies on one slightly technical definition, and the rest is simple calculus. Let us denote by f of x the fraction of the total income earned by the lowest x fraction of the populace. The domain is x goes from 0 to 1, and you should think of x as a percentage of the population, and f of x as the amount of income earned by that lowest x percent. The Gini index, denoted G, quantifies how far from a flat or even distribution the income is. What do I mean by that? Well, consider what this function f looks like. It tells you how much of the net income is being earned by what fraction of the population. A flat income would be the diagonal line where x equals y. Why? Well, the diagonal line would mean that if you look at the lowest 50% of the population, they earn 50% of all income. Of course, in practice, that's not true. They earn less. Folks at a higher income earn more and a larger percentage of the net income earned. The Gini index is a measure of how far from the perfectly flat or equitable distribution you are, and it's defined as follows. It's the ratio of the area between the flat distribution, y equals x, and the true income distribution, y equals f. It's the ratio of that and the area between y equals x and y equals 0. Well, that denominator is just telling you the area of the triangle. And since the base and the height are 1, that's 1/2. So, another way to write the Gini index is as the numerator, this area between f and x, namely x minus f of x dx, evaluated from 0 to 1, divided by 1/2, that is doubled. Let's look at this in a specific example. Let's compute the Gini index for a power law distribution, assuming that income is distributed like a polynomial, x to the n. Then, what would we get? Well, we integrate x minus f of x from 0 to 1 and double it. Well, that integral is almost trivial. It's going to be x squared over 2 minus x to the n plus 1 over n plus 1. Evaluating from 0 to 1 and then doubling what do we get? We get 1 minus 2 over n plus 1. Putting that over a common denominator yields the result of n minus 1 over n plus 1. If we look at a little bit of economic data, we find that in the year 2010, the state of New York had a Gini index of 1/2, approximately. If the income in New York State were distributed according to a monomial, then what would that monomial be? Well, we see that it would be a cubic distribution. We can't conclude that, but if it were a monomial, it would be a cubic distribution. That's a nice application.
This lesson may have seemed a bit redundant. After all, you all know the formula for the area of a triangle or a circular disk. These are the classics. But by revisiting the classics, we deepen our understanding and make it possible to accomplish more difficult works later. That will happen in our next lesson when we consider more complex planar shapes.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 31 on complex areas.
Computing areas by means of a definite integral is one of the classical applications of calculus, but it's not always so straightforward. Some shapes are too complex to be easily decomposed into triangles or rectangles. This is especially true in the context of applications where simplicity must yield to reality. In this lesson, we'll learn how to handle some of those problems by using the area element.
We begin this lesson with a quick classical example of computing the area between two curves, y minus x equals 0 and y squared plus x equals 2. The first of these is the diagonal line of slope 1. The second is a parabola that opens to the left. We need to compute the area of the region between them. I'll leave it to you to do the substitution and algebra to determine the intersection points at 1, 1 and -2, -2. And now, to compute the area, we could proceed as before by sweeping out with a vertical strip as an area element. But if we do this, then we need to decompose the region into two different parts. The area element is, on the first part, as x goes from -2 to 1, the difference in height. We need to solve for the y-coordinates. In doing so, we can write the area element as the top, y equals x, minus negative square root of 2 minus x. This height is multiplied by the width, dx. For the right-hand side of this region, as x is going from 1 to 2, then the area element is twice square root of 2 minus x times dx. And to compute the area, we need to integrate this area element. That means we're going to have to write down a pair of integrals. The integral, as x goes from -2 to 1, of x plus root 2 minus x dx, plus the integral, as x goes from 1 to 2, of twice root 2 minus x dx. Now, neither of these is a terribly difficult integral, but we're not going to do it. Why? Because there is a simpler method. We're going to reverse the direction of integration and integrate with respect to y instead of with respect to x. And so, solving for the x coordinates and sweeping out via a horizontal strip as our area element, we see there is a uniform area element, and it will reduce to a single integral. What is this area element? If we take the x-coordinate on the right, that's 2 minus y squared. Subtract the x-coordinate on the left, namely y, multiplied by the thickness, dy. Then we can integrate this area element as y goes from -2 to 1. This is a much simpler integral, and we get simply 2y minus y cubed over 3 minus y squared over 2, evaluated from -2 to 1. That equals 9/2, the area. The direction matters. If you encounter an integral that is too difficult, try reversing the direction. A related, albeit more complex example comes to us from thermodynamics in the analysis of an idealized heat engine. What happens to a gas in a chamber in something that, say, might power an automobile? Now we're going to go over a couple of terms from thermodynamics very quickly. All of these have to do with measuring what is happening to the volume, V, and the pressure, P, of the gas in the chamber. In this idealized heat engine, there are 4 stages or strokes. The first is called a combustion stage, otherwise known as an isothermal expansion. The volume is increasing, and the pressure, P, times the volume, V, is constant. Let's call that A. So in this first stroke, you're moving to the right along a curve in the VP plane, where the product is a constant. The second stroke is the power stroke, sometimes called an isentropic expansion. In this case, you're moving along the curve. P times V to the gamma equals another constant, let's say B. Here, gamma is yet another constant that is greater than 1 and depends upon the properties of the gas. The third stroke or stage is the exhaust stroke. This is an isothermal contraction in which V is decreasing and you're moving along a curve. P times V equals another constant. Let's call this one A sub 0, and we'll call the former PV constant A sub 1. Now we're moving to the left along one of these curves. The last stroke is the compression stroke, otherwise known as an isentropic contraction. Volume is decreasing, and you move along the curve. P, V to the gamma, equals a constant. We'll call this fourth constant B naught, replacing the B in our earlier isentropic expansion with B1. All right, that's a lot of setup. What's the payoff here? In thermodynamics, you trace out this region in the VP plane, and the work that the engine does over 4 strokes of a cycle is equal to the area that is traced out in this plane. And so we are motivated to find that area. If we sweep out this region, integrating with respect to V using vertical strips, it's not so simple. It seems to have several different pieces. Perhaps reversing the direction would help? No, this does not make things any simpler at all. So let's go back to integrating with respect to V. In this case, the region breaks up into 3 distinct zones, each requiring its own integral. In the first piece, we have on the top the curve PV equals A1. Solving for P gives us A1 over V. Subtracting the P value for the bottom curve means subtracting B naught over V to the gamma. That's for the first region. The second region is between 2 isothermal curves. And that gives us A1 minus A naught over V. The third region, with a little bit of work, gives us an integrand of b1 over v to the gamma minus a naught over v. Now, none of these integrals is difficult to perform. What is difficult is determining the limits of integration, because we have to find all 4 intersection points of these curves and determine their v values. I'll leave it to you to show, with not a small amount of work, that the first intersection point on the left is quantity b naught over a1 raised to the power 1 minus gamma. You can imagine how much work it's going to take to do and simplify these integrals. That's the bad news. The good news is that the answer at the end is really quite simple. a1 minus a naught over gamma minus 1 times log of b1 over b naught. If the answer is that simple, well, isn't there an easier way to do the integral? There is, but you're going to have to wait to find out. Complicated shapes require new techniques. Here's one approach. In the case where a shape is defined by a radial distance, we can use what is called polar coordinates. So if we have a shape of the form r equals f of theta, where r is a distance to the origin, theta is an angle made to the x-axis, then trying to fill out such a region by vertical or horizontal strips as an area element is likely to lead to frustration. And so, as we did in the case of a circular disk, we can use an angular wedge and sweep that around based at the origin. What will this area element look like? We'll approximate it as a triangle whose length is r, the radial distance, and whose height is r times d theta. In this case, the area element is the area of this triangle, 1/2 r times r d theta. And that is 1/2 r squared d theta, but remember r is given as a function, f of theta. Hence, we have something that we can integrate to get the area, that being the integral of 1/2 quantity f of theta squared d theta. Let's explore this in the context of an example. Compute the area between the regions r less than or equal to 2 sine theta and r greater than or equal to 1. We can clearly see that r equals 1 is a circle, radius 1, centered at the origin. I'll leave it to you to discover that r equals 2 sine theta is likewise a circle of radius 1 shifted up the y-axis. These curves intersect at 2 points. What are they? Well, by setting the r values equal and solving for theta, we see that these points are at theta equals pi over 6 and 5 pi over 6. And now we want to compute the area of the region between the one and the other by sweeping out with a angular wedge. This area element is going to look like the difference between 2 triangles centered at the origin. The area element, dA, in this case, is going to be what? Well, we take the outer area element, that is 1/2 of the outer radius squared, and subtract off 1/2 times the inner radius squared. Of course, the outer radius is r equals 2 sine theta. The inner radius is r equals 1. Paying careful attention to our inequalities. We have to perform this integration as theta goes from pi over 6 to 5 pi over 6. And so we see that with a little bit of simplification using the double angle formula, we can reduce this integral to 1 minus cosine 2 theta minus 1/2 d theta. Simplifying a little bit, we can integrate negative cosine 2 theta to minus 1/2 sine 2 theta, and the 1/2 becomes 1/2 theta. Evaluating this from pi over 6 to 5 pi over 6 gives us, with work, our answer, pi over 3 plus square root of 3 over 2. Now, these examples, though complicated, illustrate a deeper truth, namely that by changing coordinates, we can make the integral simpler. It looks like we're playing around with triangles and area elements like that, but what we're really doing is changing coordinates so that we can integrate with respect to theta. Likewise, in the problem that we didn't solve about thermodynamics, the right way to solve that problem is to change to a new coordinate system in which the associated shape becomes a rectangle. That will make things easier to handle. You're going to have to wait until you get to multivariable calculus to see how to do this properly.
Through solving, or at least attempting, some more challenging problems, we're led to a new perspective, that of a change of variables formula for planar, two-dimensional shapes. We're going to save the full exposition of those ideas for multivariable calculus, but if you'd like to see a preview, check out the bonus material. Then we'll move on to our next lesson, where we'll compute volumes.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 31, Bonus Material. When you get to multivariable calculus, you're going to learn a simpler and more fundamental approach to area elements. Recall that when we computed the area of the region between two curves, the graphs of f and g, then we used a vertical strip as an area element and integrated with respect to dx. In other problems, it became more efficient to use a horizontal strip and integrate with respect to dy. In multivariable calculus, you will take the intersection of these two, obtaining an infinitesimal rectangle and filling up the region of interest with those shapes. What is the area element in this case? If we look at a rectangular element with dimensions dx and dy, infinitesimals, then the area element dA is the product dx times dy, or if you like, dy times dx, since at this point we're not so worried about the order of things. In this case, to compute the area of this domain, let's say the domain D between these two graphs, then how would you integrate the area element? In multivariable calculus, you will write this as a double integral using two integral signs. This means that you need to integrate both with respect to dx and with respect to dy. Now, the double integral of this area element is the double integral of, let's say, dy dx. And the reason I write it in that order is that we're going to insert some parentheses and first integrate with respect to dy, then integrate with respect to dx. Now, all of the complexity in this problem is built in to how you set up the limits of integration. Let's work from the inside, moving out. If we consider integrating with respect to dy for a fixed value of x, then what are the limits on y? Well, clearly y goes from g of x at the bottom to f of x at the top. that is really what's giving you your vertical strip. And then our limits on x are x is going from a to b. Since once we've integrated out with respect to y, then we just need to perform that sweep from left to right. And now, although the notation is a bit unusual, the computation is completely elementary. Let's do that inner integral first. What is the integral of dy? Well, of course, that's just y. But we need to evaluate this. What are the limits? Y is going from g of x to f of x. Then we need to take that output and integrate with respect to dx. That leads to the formula, the integral. X goes from a to b of f of x, the upper limit, minus g of x, the lower limit, dx. And you've seen that formula before. That is one principled manner in which to derive it. You're going to see a lot more about this later in multivariable calculus and even a little bit later in this course. Well, let's take an extra moment or two and see something remarkable that we can do with this approach. Let's consider a domain D that is a round disk, radius 1. Now, we could split this up into vertical or horizontal strips and compute the area, but let's use our infinitesimal square, dA, and fill up the region in that manner. Then, what is the area, A, of this domain, D? It is, of course, the double integral of dx times dy. Now, I'm not going to fill in the limits and do that work. You've already done that in this world. You and I both know that the area of this region is pi. Now, consider what happens when we look at an elliptical region. Let's say that the minor and major axes are A and B, respectively, aligned along the x and the y axis, let's say. Then, one way that I could think about computing the area of E is how? Well, I could take my domain D and stretch it out and squeeze it into this elliptical shape. When you know a little bit about matrices and vectors, then you'll be able to specify this exactly. But for now, let's assume that this disk were made out of some stretchy material, and we've simply stretched out the round disk into this elliptical region, stretching or compressing as need be. In so doing, we have not only deformed the region and changed its area, we have deformed the area element, dA. How have we done so? Well, if you look at what is happening in the x direction and in the y directions, the radius of 1 gets changed to A in the horizontal axis and B in the vertical axis. That means at the infinitesimal level, you can think of small rectangles whose dimensions are A times dx and B times dy. And these squares will match up perfectly with the rectangles on the right. So, in this case, we could say that the area element for this region E is A times B times dx times dy. Then, integrating that area element not over E, but over D, and then pushing it over to the elliptical region, allows us to do this integral very simply. We can pull out the constants A times B, and we're left with the double integral over D of dx dy. That we know to be pi. That gives a final area of pi times a times b, and that is the area enclosed by this ellipse. Maybe you should think about what happens in that formula when a equals b equals some constant r. Then we obtain the familiar formula for the area of a circular region of radius r. More generally, what we've done in that computation, which seems like a bit of a trick, is actually a very deep idea. It is a type of change of variables formula. And that's one of the most important principles you're going to learn about in multivariable calculus. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 32 on simple volumes.
In this lesson, we'll progress from computing areas in 2D to computing volumes in 3D. Following the pattern that we used with areas, we'll begin with some of the classical shapes and consider their volume formulae. We'll look at round balls, cones, and pyramids.
When computing volumes, there's really only one formula you need to know, and that is that the volume is the integral of the volume element, and all of the difficulty lies in finding the correct volume element. The simplest example would be that of a rectangular prism of length L, width W, and height h. In this case, computing the volume element is simple if we slice along one of the three principal directions. One volume element might be W times h dx, integrated from 0 to L. Another, L times h dy, integrated from 0 to W. Or finally, L times W dz, integrated from 0 to h. All three integrals return the volume, length times width times height. For a less trivial example, consider a cylinder with base, a disk of radius r, and height h. There are several ways to compute the volume as pi r squared h. One method involves taking the associated area element for the base and multiplying by the height of the cylinder, h. As we saw in a previous lesson on area, there are several different ways to do this. We could use a lateral slice of thickness dx and obtain as a volume element 2h square root of r squared minus x squared dx, integrating from negative r to r. If instead we use an angular wedge, then we integrate with respect to theta, the volume element, 1/2 r squared h d theta. Here theta goes from 0 to 2 pi. Finally, if we use an annular area element, then associating a t variable to that, we consider as a volume element this cylindrical shell whose volume is 2 pi t times h dt. Here we integrate from 0 to r. Now moving up in complexity a little bit, consider a round ball of radius r. In this case, we're going to slice along a lateral plane. This leads to a disc-shaped volume element. But as we slide the plane back and forth over this solid ball, we see that the radius of the disk changes. It's going to take a little bit of work to figure out this volume element. In this case, since it's always a disk, the volume is the area of that disk, pi times whatever its radius is squared, times the thickness. Let's call it dx. Now, at a particular value of x, what is the associated radius? It will help to build a right triangle. in a cross-sectional view whose base is of length x, whose radius is, of course, r. What is the height? In this case, it is square root of r squared minus x squared. So, to compute the volume, we integrate the volume element. That is, we integrate pi times quantity r squared minus x squared dx, as x goes from negative r to r. In contrast with computing the area of a round disk of radius r, computing the volume of a round ball of radius r is relatively simple. This integral is very straightforward, yielding pi times r squared x minus 1/3 x cubed. Evaluating that from negative r to r leads, with just a little bit of algebra, to the familiar formula, 4/3 pi r cubed. There's more than one way to derive this volume formula. Let's look at a different method. Consider slicing up the ball into cylindrical shells as a volume element. Let's choose a radial variable. Let's call it t. And then consider a cylinder that sweeps out the volume of the ball parallel to some, let's say, vertical axis. In this case, what can we say about the volume element? Well, I claim it is 2 pi th dt. That is the area of the annular strip of thickness dt and radius t times the associated height h of the cylinder. Well, that's great, except what is h? It depends on t. Again, building the associated right triangle is going to help us out. This triangle in profile is going to have hypotenuse, r, the radius of the ball. The base is of length t, the radius of our cylinder. The height is given by Pythagoras as the square root of r squared minus t squared. But that's the height of the triangle. The height of the cylinder is this doubled. Hence, our volume element is 4 pi t, square root of r squared minus t squared dt. And to compute the volume of the ball in this alternate fashion, we integrate this volume element as t goes from 0 to r. Now, this is not so difficult of an integral. It's not quite as easy as the last one, but a simple substitution, letting u be r squared minus t squared. We see that du is negative 2t dt, and that we can rewrite this as the integral of negative 2 pi square root of u du, as u goes from r squared to 0. That integrates simply to negative 2 pi times u to the 3/2 over 3/2. Evaluating from r squared to 0 and simplifying the algebra leads to 4/3 pi r cubed. A last method for decomposing the ball and obtaining the volume would be to use a spherical volume element. This is a round shell, concentric with the ball. We're going to need to choose a variable to denote the radius of this shell. Let's call that rho. That's a letter that you'll be seeing again in multivariable calculus. In this case, I claim that the volume element is really the surface area of this shell, 4 pi rho squared, times the thickness, d rho. Now, I'm not going to justify that computation other than to demonstrate that when we integrate it, as rho goes from 0 to r, we obtain, most simply, 4/3 pi rho cubed. as rho goes from 0 to r, we have, very easily, the formula for the volume. Using this spherical shell seemed to be the simplest integral. But determining what the volume element is in terms of the surface area of that shell was maybe not so simple. The moral of this story is that the proper volume element can make the integration very, very simple. Let's switch to a different example and consider cones. You may recall the formula for the volume of a cone with a circular base of radius r and height h. Let's turn our cone upside down, putting the point at the origin of the xy plane in profile, and then consider slicing along disks that are parallel to the x-axis. All of these slices are going to be disks of some radius, and so the volume element is going to be pi times x squared dy, where x is the radius of this disk. But we want to integrate with respect to y, since our thickness, our differential element, is dy. So, writing things as we have done so with the apex at the origin of the plane, we see that the equation for the line that determines the profile of the cone is y equals h over r times x. Solving for x as r over h times y, we substitute into the formula for the volume element to obtain pi times quantity r over h y squared dy. And now, to compute the volume, we integrate this volume element as y goes from 0, the bottom, to h, the top. Pulling out the associated constants gives pi r squared over h squared. What's left is the integral of y squared dy, which is, of course, y cubed over 3. Evaluating from 0 to h yields the perhaps familiar formula 1/3 pi r squared h. Now, what happens if, instead of a cone with a circular base, we consider something else? Let's say a square of side length s. Proceeding as before by turning the cone upside down and slicing along lateral planes, we see that the volume element is a thickened square of some side length. What is that side length? If we solve for the line that constrains y in terms of x and solve for x, then we obtain a volume element that is 4x squared dy, namely 4 times quantity s over 2h y squared dy. Integrating that to obtain the volume leads to the integral of s squared over h squared times y squared dy, as y goes from 0 to h. Pulling out the constants, we are left with the integral of y squared dy, yielding y cubed over 3. Evaluating from 0 to h and multiplying by those constants out in front leads to 1/3 s squared h. You may sense a pattern here. In both cases, it was 1/3 the area of the base times the height. Well, it turns out that this is true in general for any cone with a base of area b and height h, no matter what its shape. We can, by turning it upside down and slicing, obtain copies of that base, copies that are rescaled by some factor, so that the volume element is b, the area of the base, times some factor, times the thickness dy. The question is, what is that scaling factor as a function of y? Well, let's say that you go halfway down. At y equals h over 2, what is happening to the area of the slice? The area is not decreased by 1/2. Rather, it is multiplied by a factor of 1/4. That is 1/2 squared, because we're rescaling both directions. Therefore, the appropriate volume element is b times y over h squared dy. And when we integrate that, we see that the constants b and h squared come out in front, and what's left is the integral of y squared dy. Evaluating that from 0 to h yields 1/3 the base times the height. And so we see that the real reason for that 1/3 in the volume of a cone comes from integrating y squared. That's a nice insight to this classical formula.
And so we see that the classical volume formulae still hide insights. Now we know why there's a 1/3 in the volume of a cone, and why there's a 4/3 pi in the volume of a ball. In our next lesson, we're going to turn from these simple volume formulae and consider some more complex objects.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 32, Bonus Material. Let us revisit Torricelli's law that we first saw in Chapter 3. Recall, Torricelli's law tells you about the rate of change of the height, h, of fluid in a leaking tank, where the cross-sectional area at the top is A. The version of Torricelli's law that we stated was that dH dt is proportional to the square root of h and inversely proportional to A. However, this is not the original version of Torricelli's law. Torricelli's law originally stated something about the volumetric rate of change, the flow rate going out from the tank. And this more primal version states that dV dt, the rate of change of volume, is proportional to the square root of h, with a negative constant of proportionality, since the fluid is leaking out. Now, the reasons for this version of Torricelli's law come from physical arguments. One way to get this is to assume that you have a single particle of fluid at the top of the tank, and you release it under the action of gravity. How fast will it exit the tank? Well, since distance traveled is a quadratic function of time, but velocity is a linear function of time, then the flow rate, that which depends on the velocity of the exiting fluid, is proportional to the square root of h. If we take that law as a given, how can we derive the version that tells you something about the rate of change of the height of the fluid? Well, we know what the volume V is. It is, of course, the integral of the volume element. And that volume element implicates the cross-sectional area. We can write that as the integral of A of y dy, where y is the distance from the bottom, and the limits are y goes from 0 to h. Both of these functions, v and h, are functions of time. What happens if we differentiate with respect to time? Well, I think you can see where we're going with this. We're going to use the fundamental theorem of integral calculus to show that this equals a of h, substituting in the limit, times dH dt, invoking the chain rule. This is dv dt, and we know from physical arguments that that is equal to negative kappa times the square root of h. If we solve that equation for dh dt, then we see the inverse dependence on A. Here's another problem with a very similar solution. Consider what happens if you have a beverage in a glass and you assume that that liquid is evaporating. At what rate is it evaporating? Well, you might reasonably assume that the rate is proportional to the exposed area at the top. Then, what is happening to the height of this fluid? How quickly or how slowly is it changing? Of course, this is going to depend on the shape of your glass. Well, again, we need to have some sort of relationship between the volume and the height and the exposed area at the top. And so, just like before, we will write down the volume as the integral of the volume element. The volume element, dv, is going to be a of y dy, where again, y is distance from the bottom. Then, in this case, writing the volume as the integral of the volume element, we obtain the integral of a of y dy as y goes from 0 to h, where h is the height of the fluid. As before, all of these are functions of time. And so, if we differentiate with respect to t and invoke the fundamental theorem of integral calculus, we obtain dv dt is what? A at h times dh dt. Now, what do we know about this? The evaporation of the beverage is telling you about the rate of change of volume. And so, if that rate is proportional to the exposed area, then that means that what we've computed is equal to some constant, c, times A of h, the cross-sectional area at the top. What do you notice? On both sides of the equation, we have the cross-sectional area at the top, A of h. Therefore, these terms cancel, and we are left with the result that dh dt is equal to a constant. That is, under these assumptions about evaporation, the rate of change of the height is independent of the shape of the glass. That is a little bit remarkable, and it's just one example of how being familiar and indeed dexterous with the computation of volume elements and the fundamental theorem of integral calculus can lead us to some wonderfully useful and sometimes surprising results. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 33 on complex volumes.
Computing volumes in general is not so easy a thing to do. In fact, you're going to spend a significant amount of time in multivariable calculus worrying over such problems. But, as we'll see in this lesson, some volume problems are solvable if you put the right spin on it.
The types of objects whose volumes we can compute are necessarily limited. Most solids are too complex. However, there is a class of solids for which our single variable calculus will work. These are the volumes of revolution. That is, solids obtained by rotating some two-dimensional shape about an axis, sweeping out a three-dimensional volume. There are two principal ways to decompose such an object into simple volume elements. The first is by taking slices orthogonal to the axis of revolution and progressing along the axis. This tends to lead to disk-like volume elements. Of course, the other way is parallel to the axis of revolution. Slicing about a region that is parallel leads to a cylindrical volume element in general. Let's do some examples to see these two approaches. Let us consider the solid formed by rotating a disk about an axis. One might describe this object as donut-like. What's the volume of such an object? Let's set up coordinates so that the y-axis is the axis of revolution, and that the disk that is rotated thereabout is of radius a, and the center of the disk is located a distance, capital R, away from the axis of rotation. Then, decomposing this volume by slices that are parallel to the axis of revolution gives us a cylindrical volume element. Let's compute that volume element and then integrate. The volume element intersects this disk along a vertical strip. What is the height of that vertical strip? If we use x to denote our distance from the axis of rotation, then by building the appropriate right triangle and recalling that this disk has radius a, we see that the height of this cylinder is twice square root of a squared minus quantity x minus r, quantity squared. And thus, the volume element, being cylindrical, is what? We have to take the circumference, that is 2 pi x, and multiply it by the height, twice root a squared minus x minus r squared, and then multiply that by the thickness, dx. We integrate this to get the volume. And now we have the integral of 4 pi x square root of a squared minus x minus r squared dx. What are the limits on x? X is going from capital R minus a to r plus a. This integral is not trivial, but it's easier if we perform a change of coordinates. Let u be x minus r. We're centering the coordinates at the origin of this disk. Then we're integrating as u goes from negative a to a. 4 pi times x, which is u plus r, times square root of a squared minus u squared du. If we distribute that multiplication and split it up into two integrals, then our job becomes easier, because we note that the integral on the left has an odd integrand, that is an odd function in u, that is integrated over a symmetric domain. Therefore, the former integral vanishes and goes to 0, and the only thing we have to compute is that second integral. Now, I'm going to break that up a little bit. I'm going to factor out the 2 pi r. What's left over is twice square root of a squared minus u squared du. Why have I done that? Because if I pull out that constant, 2 pi r, then what is left over is an integral that I recognize. It is an integral which computes the area of that disk, which we certainly know to be pi a squared, giving a final volume of 2 pi squared r a squared. If we repeat this computation using a volume element obtained by slicing orthogonal to the axis of revolution, then what will we obtain? This volume element is going to be an annular region, consisting of some large thickened disk minus a smaller concentric thickened disk. We need to determine the radii of this outer and inner disk. To do so, let's construct, again, some right triangles in the cross-sectional disk. And knowing that these right triangles have hypotenuse a, and height, y, then we see that the width is square root of a squared minus y squared. That means what? Well, the volume element is going to be the volume of the thickened outer disk. That is pi times quantity, capital R, plus square root of a squared minus y squared, squared. We have to subtract the volume of the inner disk. That is the disk with radius capital R minus square root of a squared minus y squared. Now this volume element is, of course, multiplied by dy, and then algebraically simplified, we see that we have identical terms in our squares, and we're subtracting the latter from the former. So by expanding and collecting terms, we obtain 2 pi r square root of a squared minus y squared minus negative 2 pi r square root of a squared minus y squared. All of that times dy. Thus, we can compute the volume as the integral of this volume element, as the integral of 4 pi r square root of a squared minus y squared dy. And we see that although we're using a different volume element in a different variable, that integrating this as y goes from negative a to a yields the same integral as we saw previously. It is 2 pi r times the integral that gives you the area of this disk, leading to, again, the final answer of 2 pi squared r a squared. Now, you should perhaps be thinking at this point that it seems as though this volume is really the area of the cross-sectional disk times the circumference traced out by the center of that disk. Well, we haven't proven that that's true, but keep it in mind. Let's move on to a different example. This one, compute the volume of a ball with a cylindrical hole drilled through it, like a bead. Let's say that we set up the y-axis to be the axis of revolution, and that our ball has radius capital R, and the hole drilled has radius A. If we choose slices that are parallel to the axis of revolution, then we have a cylindrical volume element, a cylinder with radius x that varies. In this case, the volume element is 2 pi x, the circumference of that cylinder, times the height, which is twice square root of r squared minus x squared dx. Integrating this to obtain the volume gives what? The integral of 4 pi x square root of r squared minus x squared dx, as x goes from a to r. Pay very careful attention to those limits. Make sure you understand why that is true. Doing this integral won't be so bad with a u substitution of u equals r squared minus x squared. That leads to the integral 2 pi times the integral as u goes from h squared to 0, where h is the half height of this object, if you will. We're integrating negative square root of u du. That leads to a final answer of negative 2 pi times the integral of square root of u. That's 2/3 u to the 3/2. Evaluating as u goes from h squared to 0 gives what? 4/3 pi h cubed. We can also compute this volume by choosing a volume element that is orthogonal to the axis of revolution. In this case, those slices at some constant y are annular regions. And to compute the volume element, we need to determine the outer radius and the inner radius of these annuli as a function of y. Well, in this case, the outer radius is, through a right triangle computation, square root of r squared minus y squared. The associated area of that disk is pi times that quantity squared. When we subtract off the area of the inner radius disk, that's removing pi a squared. This times the thickness dy gives the volume element. We can simplify that a little bit using what we know about this height, h. This yields the volume element, pi times quantity h squared minus y squared dy. And thus, computing the volume as the integral of the volume element yields pi times the integral of h squared minus y squared dy, as y goes from negative h to h. This is a simple integral, yielding the same answer as before, 4/3 pi h cubed. Remarkable in that a and r are not explicitly stated. Let's do one last example. Compute the volume of a vase formed by rotating the curve x equals square root of sine y plus y over pi about the y-axis, as y goes from 0 to 2 pi. Using a orthogonal slice yields disks as the volume element, disks of radius x. Thus, the volume element is pi x squared dy. Substituting in our function for x yields pi times quantity sine y plus y over pi dy. Integrating this to obtain the volume as y goes from 0 to 2 pi gives a very simple answer. We get negative pi cosine y plus y squared over 2, evaluated from 0 to 2 pi. I'll let you compute that the volume is 2 pi squared. Now, when you're doing homework problems on volumes of revolution, there are a couple things to keep in mind. The first is that there's no one formula that will do all volume computations for you. You're going to have to think about how to decompose your region. Always think in terms of whether you're slicing parallel to or orthogonal to the axis of revolution, and that will inform what you use for the associated volume element.
This ends our introduction to volume in this dimension. In our next lesson, we're going to be a bit more ambitious. We're going to ascend to higher dimensions, introduce higher dimensional shapes and volumes, and show how calculus can make sense of the geometry of the fourth dimension and beyond.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 34 on volume and dimension.
We've computed the areas of two-dimensional shapes and the volumes of three-dimensional shapes. What do you think comes next? The fourth dimension? The fifth dimension? In this lesson, we're going to do them all at once.
We begin our lesson with that timeless question: what is the fourth dimension? Well, that sounds kind of spooky. We're going to jack it up a level and answer the question, what is the nth dimension? But we're going to start at the beginning. Let's say n equals 1. What is that? Well, that's simply the real number line that you all know and love. We could coordinatize it by some variable, x. When we move up to the second dimension, well, now we have two variables to state where we are on the coordinate plane. Call it x and y. 3 dimensions is a little bit harder to draw, but no less difficult to understand. We have x, y, and z. But now, when we get to the fourth dimension, it's a little difficult to draw pictures. We can, however, simply add another coordinate. You might be tempted to use t for time or some other variable name, but why don't we just use subscripts? x1, x2, x3, x4. The reason for this being that when we move to the nth dimension, well, for large values of n, we don't have enough letters, but we do have enough subscripts. Now, drawing pictures in the nth dimension is hard. Therefore, we're going to proceed by exploring through volumes and shapes. Three simple shapes in particular: cubes, simplices, which are analogs of triangles or pyramids, and balls. Now, what do we mean when we say volume in high dimensions? Well, let's take a moment and think about that. As dimension of a object goes from 0 to n, we know what three-dimensional volume means. That's simply volume. But we also know what two-dimensional volume means. That is area. What is one-dimensional volume? Well, that is really length. Okay, you've got those three down. What is zero-dimensional volume? Well, a zero-dimensional object is simply a collection of points. How many points? That is the volume. Zero-dimensional volume is counting. And now, with these in place, we can move to n-dimensional volume, which we will call hypervolume if we're feeling epic, or we might just simply call n-volume. That will work. Let's build our intuition for n-dimensional volume by looking at an n-dimensional cube. This is going to be a cube where all of the sides have unit length. So in dimension 3, it's the familiar object. What is a two-dimensional cube? It's simply a square with side lengths 1. What is a one-dimensional cube? Well, it's got to be some interval, an interval of length 1. What's a zero-dimensional cube? It's a zero-dimensional set whose volume, or count, is equal to 1. It's just a simple point. And from that, we can extrapolate to higher dimensional cubes. But at this point, pictures fail, and we need to translate to equations. Therefore, we'll define the unit n-dimensional cube as those points in n-dimensional space whose coordinates, x sub I, satisfy the inequalities x sub I bigger than or equal to 0 and less than or equal to 1 for all I. Now, how do you visualize that? Well, it's hard to do with your eyes, but you can do it with your hands. If you think of each coordinate as an independent parameter, then it is remarkably similar to what happens when you slide an equalizer or slider bars up and down. Perhaps you've played with something like this on a sound system. Each of those slider bars is like a coordinate in the n-dimensional cube, where n is the number of slider bars. Each can go up or down, independent of the other, until you hit the boundary, where it has to stop. Now, with that in mind, let's take a look at volumes. As we consider what happens in each dimension, how do we get from one cube to the next? At each stage, what we're doing is taking the lower dimensional cube and then crossing it with an interval, making a one-parameter family of such objects. Now, in every case, the volume is 1. We're used to that in area, length times width, or in 3D volume, length times width times height. In each case, it's 1 times 1 times 1. In fact, this is really the basis for how you should think about n-dimensional volume. The surface area, well, that's a little bit harder to wrap your brain around, but we want to look at the boundary of the cube and say how much n minus 1 dimensional volume is there. So if we take a one-dimensional interval and say, what's the zero-dimensional volume of the boundary? That is, how many points on the boundary? Well, simply 2. Surface area for a two-dimensional object is what we used to call perimeter. And in the case of a square, the perimeter is 4. There are 4 unit edges. Of course, the surface area for a three-dimensional cube is what? Well, you look at each of the 6 faces and compute its unit area. Adding together gives 6. Now, in general, one could argue correctly that the surface area of the n-dimensional cube is in fact 2n, the number of boundary faces that you have. And that pattern works all the way down, even to dimension 0. The diagonal of a cube is the distance between opposite corners. We know from Pythagoras what that is for a two-dimensional cube. That's square root of 2. What about for a three-dimensional cube? Well, we would have to apply the Pythagorean theorem twice to obtain the square root of 3 as the length of this long diagonal between opposite corners. If we continue inductively, we can show that the diagonal of the n-dimensional cube has length square root of n. That's a little crazy, because for large values of n, you can have a very, very small unit cube such that the opposite corners are very, very far apart. That's a little strange. But this pattern continues down even to dimensions 1 and 0. Lastly, if we count the number of corners in an n-dimensional cube we see for a square, there's 4. For a cube, there is 8. And in general, it's not hard to show that there are 2 to the n corners. Let's move on to a different shape, one that requires some calculus to understand. This is the simplex. This is an n-dimensional generalization of a triangle or a pyramid. The unit simplex is defined algebraically as a subset of the unit cube that satisfies an additional constraint. This being that the sum of the coordinates is less than or equal to 1. Well, what does that mean in terms of our slider bar analogy? This means that you can take any of the individual bars and slide it all the way up to 1. However, you can't do this independently. If you want to move the other slider bars up, you have to do so in a way that the sum of the values does not exceed the threshold of 1. That means that this is a highly constrained set. It's not a large subset of the n-dimensional cube. It feels much smaller. We expect to see that reflected in the volume. Let's see how that works. First, let's explore a few properties, and then we'll compute the n-dimensional volume. The number of corners of an n-dimensional simplex is much less than that of a cube. The n-dimensional simplex has n plus 1 corners. What is the volume? Well, we know for a single simplex it's just a point. The number of points is 1. We know for a one-dimensional simplex, since it's the same as a one-dimensional cube, we just get a length of 1. Now, a triangle, as we all know, gives us area 1/2. When we look at a three-dimensional simplex, it's a cone over that triangle. We know the volume of a cone. It's going to be 1/3. The height, 1, times the area of the base, 1/2. Now, we start to see a little bit of a pattern here. What if I told you that the four-dimensional simplex had four-dimensional volume equal to 1/24? That's true. And knowing that, you would be convinced of the pattern, namely that the volume of the n-dimensional simplex, v sub n, must be 1 over n factorial. Now, that's a good guess. Let's see if we can show it. Our strategy for computing volumes of the n-dimensional simplices is the same as that of a cone. We're going to slice in a direction parallel to the base. And what we're going to see is that when we slice an n plus 1 dimensional simplex, what we'll get is an n-dimensional simplex whose size is rescaled by a factor of x in each coordinate, where x is the distance to the top of the simplex. So, for a one-dimensional simplex, the appropriate volume element of the slice is nothing more than dx. In a two-dimensional simplex, the appropriate area element is what? It's simply x dx. In the three-dimensional case, well, we've done this before. This is going to be 1/2 x times x dx. And in general, the difficult step is to argue that the volume element for the n+1 simplex is the volume of the base n simplex v sub n times x to the n, since we're rescaling each coordinate by a factor of x. But once we have that, and then multiplying by the thickness, dx, we can compute this n+1 dimensional volume as the integral of the volume form. That is, the integral of v sub n times x to the n dx, integrating as x goes from 0 to 1. This is a trivial integral since v sub n is a constant. We obtain x to the n+1 over n+1, evaluated from 0 to 1. That gives us v sub n over n+1. And so we can write down all of these volumes by induction and argue that v sub n is in fact 1 over n factorial. That's a nice application of simple integration. Let's move on to an n-dimensional ball of radius 1. These are a little difficult to draw. In 2D, this is simply a disk of radius 1. In 1D, it's a disk of radius 1. Well, it's really an interval of length 2. And in 1D, it is again a simple point. Higher dimensional balls are not so easy to draw. Now, how do we define it rigorously? The unit ball is defined as those set of points with coordinates x sub I between -1 and +1, satisfying the additional constraint that the sum of the squares of the coordinates is also less than or equal to 1. This is what we're used to in 2D when we say x squared plus y squared less than or equal to 1. This is simply the generalization of that. Now, in terms of a slider bar analogy, now all of the individual bars can go from -1 to 1. Each can go to the very top or the very bottom. But in between, well, you have some freedom to move the individual sliders up and down, but you can't move them all past a certain point where the sum of the squares is less than or equal to 1. Nevertheless, it feels like there's a lot of room inside of there to move around. How do we compute the volume? Well, again, for a radius 1 ball in dimension n, what is the volume going to be? In dimension 0, there's a single point, volume 1. In dimension 1, this interval has length 2. In dimension 2, well, we know the formula, pi r squared. In this case, r equals 1. In dimension 3, volume is 4/3 pi. Moving up to dimension n, well, what are we going to do here? Let's call that volume of the unit ball v sub n. And to determine what that is, let's consider what happens when the radius is not 1, but r. In this case, the length of the one-dimensional ball is 2 times r. The area of the two-dimensional ball is pi r squared. The volume, 4/3 pi r cubed. In general, having a ball of radius r in dimension n is going to give you the volume of the unit ball times r to the nth power. And that's going to be helpful for us, as we'll see. The surface area is what? Well, in the one-dimensional case, it's 2. In the two-dimensional case, we're looking at the circumference. That's 2 pi r. In the three-dimensional case, the surface area of the ball is 4 pi r squared. Do you see a pattern? Yes, it's related to the derivative. In fact, it's going to be, in the n-dimensional case, n times v sub n times r to the n minus 1. You'll be able to prove that result in multivariable calculus. What's the diameter? Well, in all cases, it's equal to 2 times r, or in the unit case, 2. Now, let's see if we can figure out what this n-dimensional volume of the unit ball, v sub n, is. Well, we're not going to be able to prove it in here. We'll do it in the bonus lesson. Suffice to say that with some work, one can show that the volume, the n-dimensional ball of radius 1, is, when n is an even number, let's say 2 times k, then the volume is pi to the k over k factorial. When n is odd, that is 2k plus 1, then the volume is pi to the k factorial 2 to the n over n factorial. Whew, that's kind of complicated. We'll show you how to get this in the bonus material. But for now, the question I want you to consider is, what happens to the volume of the unit ball as the dimension increases? Well, let's see. N, and thus k, are getting bigger and bigger and bigger. But there's a factorial in the denominator. What happens then? This means that the volume does not get bigger as the dimension increases. In fact, the volume goes to 0 as dimension increases. And it goes to 0 rapidly, since factorials beat powers. This is cause for some alarm, for some puzzlement. What does this mean? Well, let's think in terms of the difference between a ball and a cube in dimension n. Let's say we have them fight. Who wins? Well, in low dimensions, the ball of radius 1 definitely has more volume or area than the cube of side length 1. This is true in 2D. It's even true in 3D. But it is not true in all dimensions because of those corners in the cube. Those corners eventually stick out from the ball, even when the two are concentric. And all of the volume inside the n-dimensional cube lives in those corners. That's why cubes beat balls.
This lesson was neither short nor simple. It may take a little time for things to sink in. Don't worry. You're not going to be asked any questions about hypervolumes of balls on the final exam for this course. And in our next lesson, we're going to return to the more familiar low-dimensional world. But step back for a moment. Think about what you've done. We have, with rational thought and calculus, measured objects that you cannot see, smell, taste, touch, or experience with your senses. That's not a bad day's work.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 34, Bonus Material. In our main lesson, recall, we claimed that the volume of a unit radius n-dimensional ball, v sub n, is given by the following formulae. When n is even, that is, n equals 2 times k, then v sub n is pi to the k over k factorial. When n is odd, that is, 2k plus 1, then v sub n is pi to the k, k factorial, 2 to the n over n factorial. Most students would suspect that formulae this complicated must be very, very difficult to derive. That is not exactly the case. We're going to do it right now. Recall how we computed the volume of a three-dimensional ball. We sliced it by a two-dimensional plane, obtaining, when we did so, a two-dimensional ball whose radius varied according to where the slicing took place. We're going to do the same thing in this context, but instead of a three-dimensional ball, with a two-dimensional slice, we'll begin with an n-dimensional unit ball and obtain an n-1 dimensional ball as the slice. And the subtlety is in figuring out what is the radius of that n-1 dimensional slice. Our volume element for the n-dimensional unit ball, d v sub n, is an n-1 dimensional ball of some radius, r. That has volume v sub n-1 times r to the n-1. We multiply by the thickness dx, choosing some coordinate direction and calling it x. Now, what is that radius? Well, the same computation that we used in the three-dimensional case gives it to us easily. What do? We build a right triangle whose base is of length x and whose hypotenuse is, of course, 1, since this is a unit ball. What is the height of this triangle? It is r, and that is equal, by Pythagoras, to the square root of 1 minus x squared. We therefore compute the volume, v sub n, by integrating the volume element. That is, we have the integral of v sub n minus 1 times quantity root 1 minus x squared to the n minus first power dx. What are the limits of integration? This is a unit n-dimensional ball, and so we integrate as x goes from -1 to 1. Now, what do you notice about this formula? Well, first of all, we need to know v sub n minus 1 in order to compute it, but that's okay. We could proceed inductively. What is left over when you pull out that constant is simply a single variable integral, one that is entirely doable in the context of a first semester calculus course. Let us compute the value of this integral, or rather integrals, since there's one for each n. For notational convenience, let us call this integral I sub n. This is clearly a prime candidate for trigonometric substitution. And so, if we set x equal to sine of theta and dx equal to cosine theta d theta, then I'm sure you see that that square root is going to be cleared away, and we'll obtain the integral of cosine theta to the n minus 1 times cosine theta d theta. What are the limits? Well, when x is -1, theta is negative pi over 2. When x is positive 1, theta is pi over 2. And so we obtain the integral from negative pi over 2 to pi over 2 of cosine to the n. This is an integral that we have computed before. In the bonus material to lecture 28, we showed that this is equal to, well, there are two cases, one where n is even, the other where n is odd. In the n is even case, this has the value of 1 times 3 times 5, all the way up to n minus 1, over 2 times 4 times 6, all the way up till n. This value times pi. When n is odd, the evens and odds are flipped. We have a product of even numbers up to n minus 1 in the numerator. In the denominator, we have the product of odds up to and including n. All of this times an extra factor of 2. Notice the even-odd dichotomy and the change between an extra factor of pi and an extra factor of 2. This is significant. Why? Well, when we go to compute the volume, v sub n, we showed that this is equal to v sub n minus 1 times I sub n. Therefore, we can proceed inductively. Let's build a table and begin with small values of n. Now, we know the values of I sub n, we can list those, and we know the values of v sub n when n is 0, 1, 2, certainly. The zero-dimensional volume of a ball is 1, the one-dimensional volume of a one-dimensional ball is 2, and the two-dimensional volume of a unit two-dimensional ball is pi. Translating those items over to the v sub n minus 1 column, what do we obtain? From this formula, we simply multiply across I sub n times v sub n minus 1. And indeed, we see that this works with the values that we already know. What about dimension 3? I sub n is 4/3, v sub n minus 1 is pi. This tells us that v sub 3 is 4/3 pi. And that is something that you certainly know. Now we get to something that most of us don't know. What is the volume of a four-dimensional ball? Well, according to this formula, we multiply I sub 4, that is 3/8 pi, times v sub 3, that is 4/3 pi, and we obtain pi squared over 2. So the volume of a four-dimensional ball of radius r is pi squared over 2 times r to the 4th. And now we can continue inductively for as long as our curiosity and pencil hold out, obtaining various values of v sub n. At this point, one wants to look for patterns, such as the fact that there are powers of pi that increase not at every dimension, but every other dimension. Also, there are other patterns in the coefficients. If we look at what happens in the even case, it seems to be particularly nice looking. In fact, we get that pattern that we claimed at the beginning of this lesson. Namely, that in the even case, you get pi to the k over k factorial, where n equals 2k. And we see now the reason for the complexity in the odd case comes from the complexities that are in these integrals, I sub n. Now again, there are lots of things that we could say about these volumes. We can prove these general formulae by a formal induction step, but I'm going to leave that one to you. I'm also going to leave to you working out the implications of why the volume is going to 0 as the dimension goes to infinity. What I want to focus on is the question of who cares? I mean, come on, you've got volumes of n-dimensional balls, and who cares about what a ball in dimension 100 might look like? You might be surprised to learn how many high-dimensional spaces are all around you. Let's take, for example, robotics. What happens when we look at a reasonably sophisticated robot? Well, hopefully it moves. And each of its movements is tracing out some sort of dimension in its configuration space. We can try to measure all of the different joint angles, let's say. Each of these mechanical degrees of freedom leads to an extra dimension in the robot's configuration space. And if you have a highly articulated robot, one that can do lots of fine motion control, then in order to effect that control, you have to work in a potentially high-dimensional space. Things get even more interesting if we consider what happens when you have, say, a robot that is flying around, like, say, a quadrotor. How many dimensions are implicated here? Well, let's see. We have an x and a y and a z coordinate for its position. We have velocities in the x, y, and z direction. For these objects, we also have angles that determine their role, their pitch, their yaw, how they are situated in space, and how they are moving about. And if you have several of these that you are trying to coordinate into, say, a swarm to accomplish some task, then you have a lot of dimensions to worry about. And again, if one is trying to do any sort of control or differential equations on these spaces, in these systems, you are going to have to worry about things like volume in high dimensions. But really, these aren't that high. Where the dimension gets high is in data. Anything associated with large data sets, let's say stock prices or imagery data, social networks, all of these implicate many, many, many variables. And in order to provide a mathematical analysis of data sets, you're going to need to know how to work in high dimensions. Now, the tools that we've learned in this lesson are still pretty simplistic, and it's wonderful that we can reduce things like volumes of balls down to a simple one-dimensional integral. For more general problems involving high dimensions, you're going to have to take some multivariable calculus to get the right tools for solving those problems. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 35 on arc length.
After ascending to the heights of infinite dimensional spaces, we're going to come back down to Earth and consider simple one-dimensional curves. As we now know, one-dimensional volume is really just length. And we'll begin this lesson by considering the length element.
We begin our discussion of arc length with that formula that you know is coming, namely that the arc length is the integral of the arc length element. The question is, how do you determine the arc length element? Well, we think of it, of course, as a very small, infinitesimal piece of the curve. Let's say that we knew the graph and the plane, and we set up a right triangle with base dx and height dy. Then, what would the length of this hypotenuse be? Well, from Pythagoras, it would be the square root of dx squared plus dy squared. Well, that's simple enough, but how do we make that work in practice? Well, in the one case where we have an implicit curve, that is, for example, some curve where y is defined as a function of x, and we're looking at the graph, then when we write out this formula, what do we have? Well, from the chain rule, we can express dy as dy dx times dx. When we square that and follow through with the algebra, we can factor out a dx squared from under that square root sign. Of course, the square root of dx squared is dx, and we're left with dl is the square root of 1 plus dy dx squared times dx. That simple manipulation of differentials actually works. For another example, maybe we don't have a curve that's expressed in terms of a graph. Maybe we have a parametric curve where the x and y coordinates are given by some function of t. Such curves can swoop around and cross themselves in interesting ways. In this case, applying the same differential analysis, what do we have? Well, if x and y are given as functions of t, then dx is dx dt times dt, dy is dy dt times dt. Once again, we see that there's a dt squared under that square root that can be factored and pulled out, and we obtain an arc length element that is the square root of dx dt squared plus dy dt squared times dt. Let's see this put to work in an example. Compute the length of a simple circle of radius r in the plane. We'll do this parametrically, writing x as r times cosine of t and y as r times sine of t. We have to be careful to say the bounds on t are t is going from 0 to 2 pi, let's say. Then, in this case, the arc length element is square root of dx dt squared plus dy dt squared times dt. When we differentiate cosine and sine, we get, very simply, r squared sine squared t plus r squared cosine squared t dt. We see that it's easy to factor out an r squared, and applying the simplification sine squared plus cosine squared equals 1. We have an arc length element that is r dt. And to compute the length, we integrate r dt as t goes from 0 to 2 pi. And that gives us simply 2 pi r, the answer that we all know. For an example involving an implicit curve or a graph, consider the equation y equals log of sine of x, as x goes from pi over 4 to pi over 2. I don't know what the graph of that looks like, but I don't need to, since I know the formula for the arc length element. It is square root of 1 plus dy dx squared times dx. Now, when I compute the derivative of log of sine of x, what do I need to do? Well, from the chain rule, that's 1 over sine of x times the derivative of sine, namely cosine. We can simplify that a little bit. 1 plus cotangent squared x is, of course, a cosecant squared of x. Taking the square root gives an arc length element of cosecant x times dx. And now, to compute the length, we need simply to integrate cosecant x dx as x goes from pi over 4 to pi over 2. I may or may not be able to remember the integral of cosecant, but I can assure you that it is minus log of absolute value cosecant x plus cotangent x. When we substitute in those limits, pi over 4 to pi over 2, then we get minus log of, let's see, cosecant of pi over 2, that's 1, and then plus is a 0 there, and some other terms. I don't know. That's too much to do in my head, but I think that the final answer is log of quantity 1 plus square root of 2. One of the sad truths about arc length problems is that so often the integrals get messy because of that square root, and they can be pretty difficult to evaluate. But it's not all bad news. There are some very interesting problems that we can solve with integrals. One is the catenary. That is the shape of a hanging cable. Here's a fact that comes from physics. The rate of change of the slope of such a hanging cable is proportional to its length element. Now, what does that mean? If we set up some x and y coordinates to describe the curve, then what this statement claims is that the slope of the cable, which we can interpret as dy dx, changes, that is, has derivative that is proportional to the length element. That means we could write it as kappa times dl, where kappa is some constant. Now, how do we make sense of this differential equation and then solve it? It's got two derivatives. But if we let u be equal to dy dx, then we could write this as du dx equals kappa times the length element, in this case, square root of 1 plus u squared. That is a differential equation that I think we're going to be able to solve. Indeed, this is clearly a separable differential equation. And so, moving root 1 plus u squared on the left, we have on the right kappa dx. Integrating both sides yields what? Well, on the left, we're going to have to apply a substitution. And I think this is an ideal candidate for a trigonometric substitution. If we let u be sinh t, then du is cos t dt. And we have on the left the integral of cos t dt over square root of 1 plus sinh squared t. The right integrates simply to kappa x plus a constant. On the left, we have some great cancellation. 1 plus sinh squared is cos squared. The square root removes the square. The cos's cancel, and we're left with the integral of dt, namely t. If we substitute back in for u, we see that this is really arc sinh of u equal to kappa x plus a constant. If we take the sinh of both sides, then we obtain u as sinh of quantity kappa x plus c. If we set up our coordinates so that x equals 0 right at the minimal point of the curve at the bottom, then since sinh of 0 equals 0, we can say that that constant of integration vanishes, and the slope at x equals 0, that is u, vanishes also. Therefore, we have u equals sinh of kappa x. Now, this is not exactly what we were trying to find, since recall, u is the derivative dy dx. How do we get y for the shape of the curve? Well, we integrate. The integral of sinh is cos. We have to pull out a factor of kappa, and so we get y is 1 over kappa cos kappa x plus some constant of integration. Why not? That would be how high off the ground the bottom hangs. All this tells us the wonderful fact that the catenary hangs as a hyperbolic cosine. That is the shape of a hanging cable or chain. With this shape decided, let's compute the length. It is, of course, the integral of the length element, and in this case, integrating the square root of 1 plus dy dx squared dx is going to work for us. Let's set the limits to be x goes from negative L to L, where L is half of the projected length to the x-axis. Then, in this case, we need to substitute in for dy dx, but that is sinh of kappa x, leading to an integral of the square root of 1 plus sinh squared of kappa x. We can substitute in cos squared for 1 plus sinh squared. The square root goes away, and we're left with the integral of cos kappa x dx. That is, of course, sinh of kappa x divided by kappa. Evaluating from negative L to L gives us 2 over kappa times the hyperbolic sine of kappa times L. Now, what does that mean? Well, one of the things that implies is that we have exponential growth in this length of the chain, given linear growth in L, the width. That's a bit of a surprising result, but it falls out easily from what we've done. Let's take a look at an example involving a spiral. We're going to use a parametric representation like we did for the circle, but with a 1 over t coefficient out in front that causes you to spiral in as t increases. We'll let t begin at 2 pi so that we start to the right. The length element in this parametric case is the square root of dx dt squared plus dy dt squared dt. Now, this is going to involve a fair bit of differentiation using the quotient rule and what we know about sines and cosines. I'm going to leave most of the simplification work to you here. But do note that when you multiply these terms out, there's quite a bit of cancellation between the cross terms, and using the fact that sine squared plus cosine squared equals 1. In the end, you get the square root of t squared plus 1 all over t squared dt. Now, integrating that is not going to be so bad, maybe. Let's try. What we need to do is integrate as t goes from 2 pi to infinity. Now, I don't see a really good substitution at this point, but what I can do is say that the t squared is the dominant term under that square root. And pulling that out and simplifying, we get 1 over t plus something that's in big O of 1 over t squared. Now, I know that that leading order term leads to a divergent integral. When you integrate 1 over t from a constant to infinity, that diverges. We could follow the steps as we've done back in lecture 27. But what this implies is that we have an infinite spiral. That's a little bit of a surprise. There's an infinite amount of length in that simple-looking spiral. There are more surprises still. Let's say that you looked at a spiral that was not smooth, but rather based on squares descending. Let's say at each step, you're multiplying the length of the last segment by some factor, r. Well, what would you do in this case? In this case, integration becomes simply summation, and you would add up the lengths of all these segments. We recognize in this our old friend, the geometric series. And so, in this multiplicative case, it's possible to have a finite length spiral. Now, other stranger things could happen. Let's say we took a line segment and removed the middle third and replaced it with 2 line segments, each with length 1/3. Then we would have a new curve whose length is 4/3. Now, if we took each of those resulting segments, removed the middle third, and replaced with 2 smaller segments as shown, then we would be multiplying the length of the entire curve, again, by a factor of 4/3. Now, I think you can guess what we're going to do. We're going to continue this process inductively, at each stage multiplying by a factor of 4/3. In the end, we obtain an interesting object called a fractal curve, whose length is infinite, even though the curve is of bounded extent. This is the kind of interesting thing that can happen when you start using your imagination.
And so we see that even some simple one-dimensional curves can pack some surprises. Be sure to internalize the idea and computation of a length element. We're going to need it in our next lesson, where we compute surface area.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 36 on surface area.
In previous lessons, we've computed areas of flat, two-dimensional regions. But what about surface area? The area of a shape that might be wavy or curve in three-dimensional space. In this lesson, we'll see how the surface area element is related to the arc length element.
Let's begin with the computation of surface area for a very simple surface, in this case a cone, over a circle, let's say of height h, where the circle has radius r. Now, the best way to compute this is to decompose into triangles and integrate. So let's take our surface area element to be some triangle defined by a segment of the circle with angle d theta. The length of the base of this triangle may be approximated by r d theta. What is the height? Not h, but rather L, the slant length of this cone. Although expressible in terms of r and h, let's just use L. So our surface area element is 1/2 the base, r d theta, times the height, L. Integrating to obtain the surface area, we get the integral from 0 to 2 pi of 1/2 RL d theta. That is simply pi RL. That part is easy enough. We're going to put this to use in determining the surface area of a surface of revolution obtained by revolving a curve in the xy plane about an axis, let's say about the x-axis. What is the appropriate surface area element? We're going to fix a value of x and consider a vertical slice of this surface, obtaining a circle. We then thicken it up by dx. What is this surface area element? Well, this is not a cylinder. It is rather the tail end of some cone, a cone with slant length L and of radius R. Now, what we care about is not the slant length L, but rather dl, the small change in that length. That is indeed the arc length element. Now, let us use what we know about the surface area of this cone. It is pi times r times L. But how do we get ds? Well, of course, we apply the differentiation operator, and we see that ds is, in fact, pi times, through the product rule, r dl plus l dr. Now, dl, we know that's the arc length element. What do we do with dr? Well, consider the right triangle with hypotenuse L and height r. Then, if we extend things a little bit into dl and dr, then, through similar triangles, we can argue that dl over L is dr over r. Cross-multiplying, we see that L times dr is equal to r times dl, and thus we can simplify the surface area element to twice pi r dl. And this is wonderful because we know dl, the arc length element, and we know r, because r is typically given in terms of y of x, where this curve is some function y of x. Therefore, using what we know about the arc length element for such a graph, we have ds is 2 pi times y times square root of 1 plus the derivative dy dx squared dx. Let's see how this works in the context of a fun problem. Consider a round ball of radius r. Divide this ball into slices of equal width. The question is, which of these slices has the most surface area? Is it the one in the middle, or maybe the one at the end? Well, let's set things up in terms of some coordinates. If this is a ball of radius r, then it can be considered a surface of revolution, where we take the curve y equals square root of r squared minus x squared, and rotate that about the x-axis. Therefore, we know that the surface area element is 2 pi y dl. In this case, it's 2 pi times square root of r squared minus x squared times the square root of 1 plus the derivative squared dx. We've done this derivative before. It's minus x over square root of r squared minus x squared. And so, substituting that in for the surface area element, we see something that looks a little frightening. But it's not so bad. If we put the arc length element over the common denominator, r squared minus x squared, then indeed we see that that denominator cancels with the r squared minus x squared to the left. And we're left with 2 pi square root of r squared dx. That is 2 pi r dx. That is a simple surface area element. But it's not only simple, it is independent of x. It does not matter as long as your thickness is dx. That means that in the question of which slice has the most area, none of them, or rather all of them, they all have the same area. In fact, we can take this surface area element and very easily integrate it as x goes from negative r to r to obtain in our heads the familiar formula for surface area of a ball radius r, 4 pi r squared. Now that might seem like a trick or a curiosity, but if we slice horizontally and consider a slightly different setting, then we have a basis for what is called the Lambert cylindrical projection in cartography. This is a solution to the problem of how to make a map of the world where everything has the same area as on the surface of the ball, even though the map is flat. It distorts length, but not area. Let's turn to a different example. This time, we're going to take the curve 1 over x to the p, as x goes from 1 to infinity, and rotate that curve about the x-axis. This is going to give us some improper integrals. And the question is, what is the surface area? Well, let's begin by doing something a little different. Let's compute the volume of this solid obtained if we slice by orthogonal disks. Then, what do we obtain for the volume? Well, at some point x, we have a volume element given by pi times the radius, x to the minus p, squared times dx. We can integrate this to obtain the volume. That gives us the integral from 1 to infinity of pi times x to the minus 2p dx. This is a simple integral. We've done this before when we did the p integrals. When 2p is bigger than 1, we get pi over 2p minus 1. We could rewrite that as saying p is bigger than a half. Otherwise, when p is less than or equal to 1/2, we have a divergent integral, and the volume is infinite. Now that we've done volume, let's do surface area. The surface area element is 2 pi times the height, x to the minus p, times dl. We can rewrite that dl as square root of 1 plus the derivative, negative p x to the minus p minus 1, quantity squared. Now, what do we get when we integrate that? That looks like an unpleasant integral. It is an unpleasant integral, but we can at least determine whether it's convergent or divergent. How do we do that? Recall, what matters is the leading order term. We can apply the binomial expansion to that square root, since when x is very large, the p squared x to the negative 2p minus 2 is very small. And we obtain 2 pi x to the minus p times 1 plus some higher order terms. And we can be very specific about what order those are. What really matters is that the leading order term is 2 pi times x to the minus p. And therefore, we know when the integral converges and when it diverges. It converges when p is strictly bigger than 1 and diverges otherwise. Now, let's compare that surface area to what we saw in the case of volume. There are different constraints on p. For surface area, what we have is something that is finite if p is strictly bigger than 1. But for volume, we have something that is finite when p is strictly bigger than 1/2. And this leads us to the very curious result that if your value of p is somewhere between 1/2 and 1, then you can have an object with finite volume, but infinite surface area. That seems a bit counterintuitive at first, but it's very cool. Let's try an example that's a bit more finite. Let's consider simply a parabola, y equals x squared, but let's rotate it about the y-axis, as x goes from 0 to 1. That's going to give us some bowl-shaped region. In this case, we're going to want to slice horizontally and use the appropriate surface area element, 2 pi r dl. What is r? Well, in this case, it's equal to x. That is the square root of y. And in this case, what is dl? Well, it's 1 plus the derivative squared. Now, that derivative is what we need to differentiate square root of y. That gives us 1 over 2 root y. Simplifying, we get a surface area element that is 2 pi times square root of y plus 1/4 dy. And now, to obtain the surface area, we integrate this surface area element as y goes from 0 to 1. This is not too hard of an integral. We get 2 pi times quantity y plus 1/4 to the 3/2 times 2/3. Evaluating that from 0 to 1, I'll let you check that that yields pi over 6 times 5 square root of 5 minus 1. It's worth noting briefly that this problem can also be solved by integrating with respect to x instead of y. In this case, r is equal to x, and dl is square root of 1 plus dy dx squared dx. That derivative is simply 2 times x. I'll leave it to you to set up the integral and show that with a simple u substitution, it's possible to compute the exact same answer with just about the same amount of work. Sometimes it's better to integrate the other way. Let's end with one last example, a catenoid. This is what happens when you rotate a catenary about the axis. Recall the catenary, the shape obtained by a hanging chain or rope. Now we know the equation for that. It is y is some constant, 1 over kappa, times the hyperbolic cosine of kappa x plus some initial height, y naught. In this case, what is the surface area element? 2 pi y square root of 1 plus dy dx squared dx. It's easy to differentiate a hyperbolic cosine, and so we obtain a surface area element that, well, doesn't look so nice. We can simplify that square root, but in the end, we've got a cosh squared term and a cosh term. Now, this is not impossible to integrate. It is doable, but we're not going to do it here. What I do want to point out is that this is a surface that you can see. It's a wonderful example of something called a minimal surface, something that minimizes the surface area for a fixed boundary. If you took 2 wire loops and dipped them in a soap film solution and held them apart, if you do it just right, then the surface that you get will be a catenoid. And that's kind of fun to play with. Now you know how to compute its surface area.
With this, we complete our applications of definite integrals to problems in geometry. But of course, there are many other applications we could explore. In our next lesson, we'll consider a more physical application related to work.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 37 on work.
Our applications of integrals have focused primarily on geometric quantities, length, area, volume. But there are so many other applications of a physical nature that we could explore. In this lesson, we'll focus on one particular application. Now, let's get to work.
Recall the formula for the computation of work. Work is force times distance. If we take a weight, let's say, and pull it in the direction opposed to gravity, then we would be doing positive work. If we let that weight drop, then we would be doing negative work. Well, what happens in a more interesting case where, say, we're pulling that weight up over a pulley using a rope, a heavy rope, then as we pull, there is less rope that we have to support. The force, in other words, is not a constant. What would we do in that case? Well, we would think in terms of instantaneous quantities and compute the work by integrating a work element, dW. And that is the challenge. Let's look at an example involving springs. The amount of force required to displace a spring varies in terms of how far you've pulled it, the displacement, x. The force varies with that. In what manner? Well, it may be linear. The simplest type of spring is called a linear spring, and it satisfies the law that the force as a function of displacement x is a constant kappa times x. This is called the spring constant. This is sometimes known as Hooke's law, but not all springs are linear. You may have a hard spring, like in a shock absorber, where the amount of work has a linear term, but then a positive, higher order term as well. Or you may have a soft spring, which is sublinear. It has some linear term that is valid for very small values of x, but then decreases. The spring gets easier to pull. In either case, the work element is what? Well, we need to think about an instantaneous or infinitesimal change in displacement, dx. And then the work is that force, F at x, times the displacement, dx. And so we can compute the work done in pulling a spring by integrating this work element, f of x dx. Let's look at a slightly different example, this one involving liquids and pumping. How much work does it take to pump liquid from a tank? Let's say you pull it up and pump it out at a height of h from the bottom of the tank. How would you compute the work done in this case? We're going to have to make a few assumptions. First of all, let's assume a constant weight density, rho, for our fluid. Then our tank is going to have some cross-sectional area, A, as a function of x, where x is, let's say distance from the bottom of the tank. Then, what is the work element? If we take one slice of fluid at this level x, there's some force involved in moving that up. How much? A distance, h minus x. That's the distance from that slice to where the pump exits. That's how high against gravity we have to move it. Now, what's the force in this case? It's the weight density, rho, times the volume element, where the volume element is equal to what? Well, the volume element, as we know, is the cross-sectional area, A of x, times the thickness, dx. Therefore, we can compute the work in this case by integrating the work element by taking the integral of rho times A of x times h minus x dx. But don't memorize this formula. When you see a problem of this form, work it out for yourself. You might be pumping the fluid up. You might be pumping the fluid to a lower level. You're going to have to work out the work element. This type of reasoning is valid in many different contexts. Let's say moving earth as opposed to pumping a fluid. Consider a hole that is being dug by two workers who take turns in digging the dirt and moving it to the top. How deep should the first worker dig in order to divide the amount of work done evenly? Is it a fair deal to go halfway down and then let the second guy do the second half? Or maybe not. Let's make some assumptions. Again, as in the case of a fluid, we'll assume a constant weight density, rho, for the dirt. Let's say that our hole has to go to a depth, capital D, and that the hole has some fixed cross-sectional area, A. We're not going to say what that shape is. We're just going to keep track of the area of that cross-section. In this case, what is the work element? Well, we have to take the force, that is, the weight of the slice, rho, times A, times dx, times the distance that that slice of earth has to be moved. That distance is x. If we denote by x, the distance from the top of the hole to the layer where we're considering. Then, what is the work? The work is the integral of the work element. That is the integral of rho a x dx as x goes from 0 to d. This is easily integrated to 1/2 rho a d squared. That is the total amount of work to be done in digging the hole. Now, if the two diggers divide the work evenly, then the first one has to do 1/2 of that work, digging down to a level d tilde. And so let's integrate from 0 to d tilde. This same function will get, of course, 1/2 rho a d tilde squared. If that has to be half of the work, then we set it equal to 1/4 rho a d squared. Canceling and solving for d tilde, we obtain d over the square root of 2. That means to divide the work evenly, the first worker should dig a little more than 70% of the way down because of the extra work that is required to get to the bottom. Let's consider a similar example, this one involving moving bricks and building a pyramid. Let's say that you start off with a collection of bricks that are at the ground level. How much work would it take to stack them into a pyramid? We'll make the standard assumptions that all of your bricks start off at the bottom, that we're building a pyramid with a square base, and in order to use calculus, we're going to assume that the bricks are very, very small and of a constant weight density, rho. Then, in this case, modeling our pyramid by some smooth object, let's say of side length s at the bottom and of height h. We'll set up a coordinate system where y is the distance from the bottom. Then, in this case, the work element is the weight of a slice through the pyramid at height y times y, the distance that you have to raise the level of the bricks. Now that force element is really rho times dv, the volume element, And that, again, can be computed as we've done in the past as s squared, the area of the base, scaled by the factor of 1 minus y over h quantity squared times the thickness dy. And now we have something that we can integrate in order to compute the work. The work is the integral as y goes from 0 to h of rho s squared y times quantity 1 minus 2y over h plus y squared over h squared dy. That's a simple polynomial integral that gives us, in the end, rho times s squared times h squared times 1/2 minus 2/3 plus 1/4. That is, with a little arithmetic, 1/12 rho s squared h squared. If you compare that to the volume of the pyramid, you see that it's 1/4 the volume times h. That h factor is telling you that you've got to raise those bricks up to that level, and that takes work. Let's look at some examples that we began the lesson with, thinking in terms of ropes. How much work is it to pull a rope up over a pulley? Well, we have to make some assumptions about how much the rope weighs. Let's assume that we have a length L and a weight density rho. Now let's think if we were to break this rope up into infinitesimal pieces of length dl, then we would have to raise that up by some height. Let's call it L. Then the work element is rho times the length element, dl, that's giving you the weight, times the distance, capital L, that we have to move. To get the work, we integrate this work element. That's a simple integral going from 0 to little l. It gives us 1/2 rho times little l squared. Now, we've assumed that that rope just hangs off the edge. What if the rope were a bit longer? Let's say that there's a table, a height h from the pulley, and there's a long segment of rope that maybe rests in a bucket at the bottom. How much work would be done in this case? Well, we're going to have to use our collective head and think about what we've done and how to generalize it. If little l is less than or equal to h, our previous analysis holds. In the case where little l is bigger than h, then let's think. It is equivalent to computing the work done in pulling up a rope of length h. We've already solved that problem. That's 1/2 rho h squared. All of the leftover rope is at the bottom of the bucket, and we have to move it wholesale to the top. We can consider that as just a fixed weight that is equal to rho times the leftover length, L minus h, times the distance traveled, h. That gives us a final answer of 1/2 rho h times quantity 2L minus h. There's really no end to the type of tricky problems one can come up with. One of the classics is the leaky bucket problem. How much work does it take to pull up a bucket whose weight is changing as a function of the height, x, off the ground? In this or any similar tricky setting, what you need to do is determine how much weight you are pulling as a function of, let's say, x, the height off of the ground. Once you have that weight, then you can compute the work element by considering, what am I integrating with respect to? Well, in this case, x. How much force is there at that particular value of x? That's going to be f of x. When you multiply f of x by dx, you get the work element, which you need to integrate to get the work. When you do your homework assignment for this lesson, you'll get a lot of practice setting up these kinds of problems. But in all settings, there is no single formula for you to memorize. Don't copy formulas from a book and try to memorize them. Work out DW for yourself based on the particulars of the problem and then integrate.
The techniques that we've developed for computing a work element are broadly applicable to many problems in the physical sciences, the engineering sciences, and the social sciences. In our next lesson, we'll fly through a collection of such applications and show how to compute elements.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 38 on the elements.
In the past several lessons, we've seen examples of area elements, volume elements, length elements, and more. What other differential elements can we integrate to solve problems? In this lesson, we'll focus on several examples that range from physics to finance.
By now, I'm sure you've discerned our procedure for computing the definite integral. First, determine the appropriate differential element, du, and then integrate to compute u. Now, we've done this in several contexts: area, volume, surface area, length, and work. The question remains, what else does this method apply to? There are many, many things. In this lesson, we'll take a look at a few. Let's begin with mass and consider, what is the mass of a pen? Well, a pen is composed of many parts. We could compute the mass of each and add them together. Or, using calculus, we could set up a coordinate x along the pen and consider slicing it into thin pieces and compute the mass of each. This would give us what we might call the linear density, rho, of this object. The linear density is the rate of change of the mass as we change the coordinate. Now, for an actual pen, this might be a discontinuous function. However, given that linear density rho is a function of x, we could compute the mass element, dm, as rho of x, that linear density, times dx, that length element. Then, of course, the mass is the integral of the mass element. Let's consider a bigger problem. What is the mass of the Earth? We're going to consider the density as a function of the radial coordinate, r, the distance to the center of the Earth. In this case, we know that the density changes as you move from the inner core to the outer core, to the mantle, then the crust, and then the atmosphere. This, however, is not a linear density, but a volumetric density. It would be measured in, say, grams per cubic centimeter or something of that form. In this case, what is the mass element? Well, if we choose a very small segment of the radial coordinate, that is dr, then we would have the volumetric density at that r value, but it would not be times dr. Rather, it would be times dv, the volume element, since this is volumetric density. And so the question is, what is the volume element? Well, that is the surface area of the sphere of radius r, 4 pi r squared, times the infinitesimal thickness, dr. This gives us the mass as the integral of the mass element. That is the integral of 4 pi r squared times rho of r, dr. r. This would be measured, of course, as r goes from 0 to 6,400 if we were doing this in terms of kilometers. Let's switch to a different topic, that of torque, which you've certainly experienced, even if you've never learned formally. If you extend your arm and apply a force or a weight to it, you feel torque about your shoulder. The magnitude of that torque depends on the magnitude of the force and the distance from that force to your shoulder. The torque is equal to the force, really the perpendicular force, perpendicular to your arm. That force times the distance between where the force is applied and your shoulder. Now that is true for a singular force, a force applied at one point. What happens if we have a weight that is variable, that is distributed across your entire arm? Maybe we would specify this by some linear mass density function, rho, like we did in the case of the pen. Then let's compute the torque in terms of the torque element, dt. dt is going to be the distance, x, times the force element, df, the amount of force applied at x. What is that force element? Well, force is mass times acceleration. The acceleration is g, the gravitation constant. The mass, however, is a mass element, dm. And dm is computed as we have done before in the case of the pen, as the linear density, rho of x, times dx. Putting all of these together, we can obtain an integral for the torque as x times g times rho of x dx integrated over the arm. Sometimes we'll collapse g and rho of x together to give something called a weight density. Now, you don't have to memorize this formula, but you have to know how to reason in terms of elements in this manner. Let's think a little bit more about force, and in particular, the force of a fluid on a tank. Now, if we're given a weight density for that fluid, let us call this rho as well. Then, if we set up a coordinate system, x, that represents the depth from the top of the fluid in the tank, then capital P is going to represent the pressure. What do we mean by pressure? Well, there's a little bit of physics that goes on here. For the moment, you should think that pressure depends on the density of the fluid and the depth. Now, I can argue that that pressure is really the product of these two. You can see that that's reasonable if you think about how much pressure is at the bottom of the tank versus at the top. You could see that by, say, poking some holes in the side of a tank and seeing what happens to the water that is pushed out by the pressure. All right, well, given that as a backdrop, how can we compute the force that that water or fluid exerts on the side of the tank? Well, that's going to depend on all of these terms. Pressure can be thought of as force per unit area, and that leads us to the differential formulation that the force element, dF, is P, the pressure, times the area element, dA, on the side of the tank. We can expand that out further as rho times x times dA. And this allows us to integrate to obtain the force. The force is the integral of rho times x times dA. Let's put this to use in an explicit problem. Compute the net force on an end cap of a full radius r cylindrical tank. So consider a cylinder on its side, fill it with fluid. What happens at the end? Well, the pressure is increasing as you go down, but the area element is changing as well. Let's take a look at the end of that cylinder head on It's a radius r disk. X is going to be our coordinates measured from the top of the tank. We'll be integrating with respect to dx, obtaining a horizontal strip as an area element. It's going to be easier if we change coordinates to u, where u is equal to x minus r. In this case, u is going to be centered at the middle of the disk, but du will be equal to dx. In this case, the area element is given by what? Well, with a little bit of help from a right triangle, we see that the area element is twice square root of r squared minus u squared times the thickness, du. The force element is the pressure times the area element. Recall that pressure is rho, the weight density, times x, the distance from the top. Now, x being u plus r, and dA being twice root r squared minus u squared du gives us our entire force element. To obtain the force, we integrate the force element as u goes from negative r to r. The resulting integral allows us to pull out the constant weight density, rho. As we've seen in similar integrals in the past, what is going to work best is to split this up into two integrals, distributing the multiplication over the addition, and noticing that one of these integrals has an odd integrand, integrated from negative r to r. Therefore, one of these integrals goes away, and we're left with the second, rho times r times the integral from negative r to r of 2 root r squared minus u squared du. That is, in fact, the area element for the disk. And so we obtain rho times r times the area, pi r squared, yielding a net force of rho pi r cubed. Let's turn to a financial example, the concept of present value, namely, how much is tomorrow's money worth today? We can answer that if we reverse the question, because if we assume a fixed interest rate of r and continuously compounded investment, then we know from our work on simple differential equations that money grows exponentially with an exponent depending on r, the interest rate. And so, if instead of considering how money today grows, we take money in the future and say, how much money would we need today to invest to get that? Then we can argue that a certain amount of money at time t is worth that amount times e to the negative rt right now. And that allows us to discuss the present value of an income stream, I of t, that depends on time. Given that rate of income, then what is the present value? How much money would that be worth if you had it all today? Well, we can express this in terms of the present value element, dPV. This is going to be e to the negative rt times I of t dt. And so, integrating this, we get the present value. This is simply a small collection of the many possible examples of computing elements in order to integrate and solve problems.
We've gone through quite a number of different examples of applications, but we've not covered everything. Now, there's no need to learn every possible application that's out there. What one really needs to know is the procedure by which we solve these problems using integrals. In our next lesson, we're going to turn to a different class of problems that can be solved through integrals, that of computing averages.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 38, Bonus Material. Of those topics covered in our main lesson, perhaps the most challenging is that of present value. To reiterate, let's say that I were to give you $1,000 in 10 years. How much would it be worth to have right now as an equivalent, assuming that you took that money and invested it at a fixed interest rate? Well, given what we know about such investments, it would be worth that amount of money, $1,000, times e to the negative RT, where t is 10 years. That's how much it would be worth right now. But instead of some fixed amount of money to be given at some fixed future time, what happens if you have an income stream, a certain amount of money that's coming in over time and perhaps varying? Well, to solve that more challenging problem, we integrate the present value element. Let's see how that works in a specific example. Which of the following income streams would be better for you in terms of having greater present value? Let's say I give you the choice between earning income at a fixed rate, I of t is equal to some constant c, or I say, well, you get less money at the beginning, say 1/3 c, but the amount of money that you're getting increases over time linearly. Let's say I of t equals 1/3 c times quantity 1 plus RT. Which would you choose? In the second case, there would be a time in the future where you're making much more money than that fixed constant rate, c. Well, let's compute the present values and find out which is better. We'll begin with the first income stream. I of t is a constant. In this case, the present value element is e to the negative RT times I of t dt. That is c e to the negative RT dt. If we integrate that, well, let's see, what are our bounds on integration? It wasn't said what sort of time frame we had, so let's assume a very, very long lifespan and integrate as t goes from 0 to infinity this present value element. This integral is not so hard. The constant comes out, we integrate e to the negative RT and get e to the negative RT over negative r. When we substitute in t equals 0 and take the limit as t goes to infinity, then we get simply that constant c over r. That is the present value of this infinite income stream. Let's see how this compares with an income stream that is linearly growing, but which starts off much lower. If we have I of t equals 1/3 c times 1 plus RT, then our present value element is that same income stream times dt times e to the negative RT. Now, integrating that is going to be a little bit more challenging, but not so bad. It breaks up into two integrals. The first is 1/3 c e to the negative RT dt. But that's really the same integral that we just did for the constant income stream, but the constant in front is 1/3 c. Therefore, the first integral evaluates to c over 3r. For the second integral, it's going to take a bit more work. Let's pull out the constant, cr over 3, and then integrate what is left over. Using integration by parts, we're going to let u be equal to t and dv be e to the negative RT dt. I'm going to leave some of the details to you at this point to show that what we get is u times v, that is t over negative r times e to the negative RT, evaluated from 0 to infinity. what we get when we subtract the integral of v du is adding the integral of 1 over r e to the negative rt dt. And that, of course, is a simple integral. The first term, the uv term, vanishes at those limits, and we're left with an integral that we can easily solve. The net present value of the second income stream is c over 3r plus cr over 3r squared. That simplifies to 2/3 c over r. When we compare that to the fixed income stream, which had a present value of c over r, we see that this linearly increasing stream is worth only 2/3 as much over time. That is not an obvious conclusion. Now, there are many, many other examples in finance and economics that work well when argued in terms of elements. I'll leave it to you to think about what future value of an income stream might be. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 39 on averages.
What's an average? An average is something that's in the middle. That doesn't sound very mathematical, but that intuition will help you as we consider what it means to take the average of a function.
Averages are both ubiquitous and intuitive. If someone were to ask, say, what is the average unemployment rate? Well, you might get out the graph and eyeball it. Try to pick a number that's sort of in the middle. That's the way it feels like it ought to be. But, of course, an average depends on a couple of factors. First of all, it depends on the interval over which you are looking. If, in the case of unemployment, you change your time interval, then you might have very, very different results. And, in fact, the function that you're trying to average might look very, very different. And as the variation of that function increases, it becomes harder to see what we actually mean when we say average. And so we need a definition. Now, our intuition says that the average of a function f over an interval from a to b should be the constant value where the area above and the area below balance out or are equal, let's say about there. We would denote that average by the symbol f bar, the bar over the top, meaning the average. We can write out an integral form for this intuitive definition, namely that the integral as x goes from a to b of f minus f bar dx equals 0. Now, let us solve this equation for f bar. Integration is linear, so we can move the integral of f bar over to the right-hand side, but by definition, f bar is supposed to be a constant, just a number, so we can pull it outside of the integral. And now, solving for f bar, we get the integral of f dx over the integral of dx, both integrals running from a to b. Now, you've probably seen what comes next, namely, we evaluate the denominator to be x evaluated from a to b, that is b minus a. And so one typically writes f bar equal to 1 over b minus a times the integral from a to b of f dx. That is a great definition. It's fine, but it's not optimal. The better definition is in terms of the ratio of the integral of f to the integral of 1. And why is this so much better? Well, instead of your integration domain being the interval from a to b, we could consider an arbitrary integration domain, d, and still have a nice definition for the average f bar. For example, if D is a discrete set, and your F is really just a sequence of values, like, say, test scores, then you know the classical formula for the average. In this case, it's the sum of these F values divided by N, the number of scores. But of course, we could rewrite that as the sum of the F values divided by the sum of 1. As you're going from 1 to n, that's giving you your denominator. And this really fits into the same category of definition, since a sum is really just an integral for a discrete set. Now let's look at a few examples. Let's compute the average over the interval from 0 to t of 3 classical functions, monomials, exponentials, and logarithms. For the monomial, for x to the n, what we have to do is integrate x to the n dx from 0 to t, and then divide by t. This is simple. You can really do it in your head. What do you get? You get t to the n, that is the function evaluated at the right-hand endpoint, divided by n plus 1. That's the average value of x to the n over this interval. What about the exponential? E to the x goes beyond polynomial growth. Well, this too is an integral that we can do in our head. But notice what you get. You get the right-hand endpoint, e to the t, minus 1, divided not by any n, but by t. So it's as if all the growth that happens in the exponential function happens right at the end. Now, lastly, for the logarithm, we're going to have to change our lower integration value to 1 rather than 0. But notice what happens. When we integrate log of x, we get x log x minus x, through integration by parts, if you like. When we evaluate this, we see that the average value for log of x on the interval from 1 to t is exactly log of t minus a little bit. This is, again, telling you how slowly log of x grows. Its average value is almost equal to the right-hand endpoint. That's pretty cool. Let's do another example. What is the density of the Earth? By which I mean the average density, since it changes. Recall, we know a little something about the volumetric density function, rho, as a function of r, radial distance. Now, you might be tempted to look at this graph and try to eyeball it and figure out the average density there. But be careful. We have to use this integral formulation. Rho bar is not the integral of rho of r dr over the integral of dr. That is not what it is, because of course rho is a volumetric density. And so our integration must be done with respect to the volume form. Rho bar is the integral of rho dv over the integral of 1 times dv. Now, rho dv, as we recall, is really just the mass element. And so, in retrospect, it's really kind of obvious that what we would do to compute the average density is compute the mass, the integral of dm, over the volume, the integral of dv. And you can write that out more explicitly if you wish. Let's turn to another example, this time involving blood flow through a tubular vessel. There is something called Poiseuille's law that tells you how the velocity of the fluid varies with respect to location in the cylindrical vessel. If we look at a cross-section that is going to be a disk of radius capital R, there's some maximal velocity, but the velocity is going to be a function of the radial distance, little r. This is going to be a quadratic function. Poiseuille's law says that the velocity, v, as a function of radial distance, r, is p over 4 mu l times quantity, big R squared, minus little r squared. In this case, p is a pressure, mu is a viscosity, l is the length of the vessel. Don't worry about all that stuff. It's just constants in this case. What we are going to worry about is the average velocity, v bar. Now, in this case, what do we integrate with respect to? It's got to be with respect to the area element, since we're taking a cross-sectional area. V bar is the integral of v dA over the integral of dA. In this case, dA is an annular strip with constant little r, that is 2 pi r dr. Now, plugging in our formula for v, what do we get? Well, first of all, the denominator gives us a pi r squared. That we know. And so what we have left is the numerator, that is the integral, as little r goes from 0 to big R of this constant, p over 4 mu l times quantity, big R squared minus little r squared, times the area element, 2 pi r dr. Now we can simplify that integral quite a bit, pulling out the p over 4 mu l constant, canceling the pi's, pulling the 2 outside, and then what do we have left? Some big constant times a simple integral. We have to integrate big R squared times little r dr. That gives big R squared little r squared over 2. And then we have to subtract off the integral of little r cubed. That's little r to the 4th over 4. Evaluate from 0 to big R, and what do we get? Well, we get something that looks a little complicated at first, but is not so bad. Some of the big R's and the coefficients cancel, and we're left with p over 4 mu l times big R squared over 2. If we consider our initial velocity profile, we see that this is really just 1/2 times the maximal velocity at the center of the tube. That's a nice result. For our last example, consider what happens when you plug something into the wall. With alternating current, the voltage is going to be sinusoidal. The voltage as a function of time is going to be some constant, Vp, times sine omega t. This constant, Vp, is the amplitude or peak voltage. Omega is giving you some sort of frequency of oscillation. The period is going to be defined as 2 pi over omega. Now, the question is, what is the average voltage? Well, the problem is, over every period, if we compute the average, we wind up integrating a sine function over an entire period from 0 to 2 pi, as it were. I'll let you do the computation to see that the average voltage is 0. That is totally useless for our purposes. So what we do is define a different type of average. This is called the root mean square in some circles. Sometimes it's called the quadratic mean. The root mean square is defined as follows. Square your function f, take the average of the square, and then take the square root of that. So this square root of the average of the square will give us something that is non-zero, because that squaring makes all of the negative terms positive. In the case that we looked at before, the root mean square voltage, VRMS, is what? We square the voltage, Vp squared times sine squared omega t. Then we average that, taking the integral from 0 to 2 pi over omega and dividing by that length, 2 pi over omega. Then square rooting. Now, this integral is not so bad, we can use the double angle formula and take advantage of the fact that we're integrating over a full period so that that cosine term integrates to 0. Then we're left with the square root of omega over 2 pi times vp squared times 1/2 t, as t goes from 0 to 2 pi over omega. Well, that evaluates simply enough and, wonderful to say, cancels the period, and we're left with vp over the square root of 2. Now, in practice, that works out to about 71% of the peak voltage. That's what the root mean square is. So if you see something that is labeled at 120 volts, what you're really getting is that root mean square voltage. The peak voltage is actually bigger, almost 170 volts. This lesson should lead you to wonder what other kinds of things can be averaged. Can you average locations or points on a map? What happens when birds fly in a flock? They seem to do so with a great deal of coordination. What they are often doing is simply averaging the orientations or the directions of their neighbors. Fish do similar things. What other kinds of things can be averaged? Can we average things like faces? Can we take a collection of human faces and compute an average? In what way would that be like an integral? These are all excellent questions that, with enough mathematics, you can answer.
We now know how to average a function over a domain, and we've seen hints that there are more interesting types of averages out there. In our next lesson, we'll look at what it means to average a collection of locations or positions. Some of the integrals involved are going to be a bit intricate. You might want to take a look at the Lecture 31 bonus material before beginning.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 40 on centroids and centers.
Averages appear in many guises and shapes and sizes. In this lesson, we're going to look at how to compute average positions. This will lead to the notion of centroids and centers of mass.
How do you compute an average location? Well, this starts off simple enough. If I say, what's the average of 2 points? Well, one draws the line segment and picks the point in the middle. You could probably use some basic geometry to determine the average of 3 locations or the average of 4 locations. But what would you do if asked to compute the average of an entire region? Well, this requires thinking in terms of calculus, breaking that region up into infinitesimal elements, and then computing an average. And that's exactly what we'll do in defining the centroid as the average location in a domain. Let's call that D. In this case, if we set up x and y coordinates, then we would characterize the centroid in terms of its coordinates, x bar and y bar. That notation is chosen to help you remember the definition. X bar is the average x coordinate over the domain. That is, the integral of x over d divided by the integral of 1 over d. Y bar, correspondingly, is the integral of y over d divided by the integral of 1 over d. In higher dimensional settings, I bet you can guess what the formula is. We're going to use the perspectives from the bonus material in Lecture 31 to compute these integrals, dividing the region not into strips, but rather into infinitesimal rectangles of dimensions dx and dy, and then averaging over those. The notation that is most useful to us is that of a double integral or an iterated integral. The denominator in both of these cases, being the integral of 1 over the domain, is really the integral with respect to the area element. If you integrate dA, what do you get? Well, you get, of course, A. So one way to write these formulae for the centroid is as 1 over A times the integral over D of x dA or of y dA respectively. Let's see how that works in the case where our domain is a region between two curves, g on the bottom and f on the top, as x goes from A to B. Then in this case, the area element is going to be an infinitesimal rectangle of dimensions dx and dy. Now, in this case, if we look at the formula for x bar, that is the double integral of x with respect to area over the area, then what do we get? Well, dA is really the area of this infinitesimal rectangle, that is dx times dy. Now we're going to write that in the opposite order, dy times dx. And the reason for that is we're going to perform these integrals one at a time. Double integrals look scary. They're really not. You just do it one at a time. The trick is determining the limits of integration. When we integrate with respect to y, the lower limit is g of x. The upper limit is f of x. When we integrate with respect to x, the limits are x goes from A to B. Now, when we do so, that's really integrating out to give a vertical strip when you integrate with respect to y, and then sweeping from left to right. Let's perform those integrals. It's not so bad. What is the integral of x dy? Well, from the perspective of y, x is just a constant, so we can move that outside. And now, all we have to do on the top and the bottom is integrate dy. That, of course, gives us y. We have to evaluate that from g of x to f of x. When we substitute that in, we get simply f of x minus g of x. Now, that's just the first integral that we've done. We still need to do that outer integral with respect to x. And so we obtain a formula for x bar as shown. It looks a little complicated, but notice that on the bottom, what we've really got is the area between those two curves, our familiar formula. So we can rewrite this as x bar equals 1 over a times the integral as x goes from a to b of x times quantity f of x minus g of x dx. This is a formula that is worth knowing. You might think that the same formula holds for y bar, but it's a little bit different. There is one point at which these computations differ dramatically. That is, in the numerator, when we first integrate with respect to y, we're integrating y dy instead of x dy. Of course, that integral is easy enough. It's y squared over 2, but it makes the final formula qualitatively different. Of course, the denominator is the same. It integrates to give you the area. But when we consider what is happening in the numerator, our final formula is y bar equals 1 over a times the integral as x goes from a to b of 1/2 times quantity f of x squared minus g of x squared dx. So many students try to memorize this formula and mix it up or fail. Remember how it's derived. Remember that it's the 1/2 y squared evaluated from g to f, and you'll be fine. Let's look at this in a specific example. That is, we'll take a quarter disk of radius r in the plane. We have to compute x bar and y bar. Well, this is the region between two curves, where on the top we have y equals root r squared minus x squared. On the bottom, of course, we have y equals 0. To compute x bar, we take 1 over the area, that is 4 over pi r squared, since it's a quarter circle, times the integral as x goes from 0 to r of x times f of x minus g of x, that is x times root r squared minus x squared dx. Well, that is a doable integral, but let's wait a moment, because if we use the formula for y bar, we obtain a different integral. We get 4 over pi r squared times the integral from 0 to r of 1/2 quantity root r squared minus x squared squared dx. In the case of y bar, the integral is simpler. That square root goes away, and we can simply integrate r squared minus x squared dx. That gives r squared x minus x cubed over 3. Evaluating that from 0 to r and accounting for the constant that we pulled out gives an answer of 4r over 3 pi. Well, so much for y bar. How are we going to compute the integral to get x bar? Well, if you consider what this shape looks like and the symmetry that is present, you can argue that the centroid would have to lie on the line where y equals x. And so we have computed x bar as well as y bar. This points to a more general principle that centroids respect the symmetries implicit in a domain. If you have an axis of symmetry, the centroid lies along it. If you have 2 axes of symmetry, the centroid lies in the intersection. Unfortunately, not all domains have nice symmetry properties. Consider a triangle, let's say a right triangle, of height h and length l in the plane defined by the hypotenuse, given by y equals h over l times quantity l minus x. What's the centroid of that region? Well, we can write down our formulae for x bar and for y bar. It's simple enough in this case. What we have to integrate to obtain x bar is 2 over hl, that's 1 over the area, times the integral as x goes from 0 to l of h over l times quantity lx minus x squared dx. That's a simple polynomial, easy enough to integrate. Substituting in l gives us, after a little bit of simplification, 1/3 l. So the x-coordinate of the centroid is 1/3 of the way from the left. If we compute the integral for y bar as well, we'll see that we again get a quadratic polynomial that we integrate to get a cubic. There's a lot of substitution that's going on, but in the end, it simplifies to give us y bar equals 1/3 h. Now, of course, this is as it ought to be, because there really is something of asymmetry going on here, in that if I rotated and flipped the triangle, I would obtain a new triangle with h and l reversed. And so there must be this relationship between x bar and y bar. They've got to have the same formulae, flipping out l and h. But in fact, we can say more. Let's say we shear that triangle to the left or to the right. What happens to the y-coordinate of the centroid? Well, really, nothing. We're not changing any y-coordinates of area elements, so the average is the same. And what we obtain is that for any triangle, its centroid is located 1/3 of the way in from each of the 3 sides. That is where the centroid is at. And considering it from a slightly different point of view, this is what one obtains by focusing all of the mass, if you will, at the 3 vertices and averaging the coordinates of those 3 vertices. You can see how our formula falls out immediately from that. And in fact, this perspective of focusing mass is common in physics when we're trying to represent locations of large objects, or in chemistry where we're trying to represent locations of very, very small objects. This leads us to the notion of a center of mass, where we're weighting the average of the locations by the mass element. The formulae are very familiar. The coordinate for x in the center of mass, x bar, is the integral of x over d divided by the integral of 1 over d. But instead of integrating with respect to area, we're integrating with respect to mass. This would give us a formula of 1 over m, the mass, times the integral of x dm. Let's look at a simple example where it's one-dimensional and the mass element, dm, is some linear density, rho of x times dx. Then, in this case, let's say x is going from 0 to L, and the density varies quadratically in x. You could imagine a situation in which the cross-sectional areas are getting bigger according to a quadratic relationship. What would the center of mass be? Well, we have to compute the mass element that has thickness dx, and then density, some constant kappa, times x squared. Plugging this into our formula for x bar, what do we get? Well, we get a couple of integrals that are easy enough. Notice that the constants kappa cancel, and we obtain 1/4 x to the 4th from 0 to L divided by 1/3 x cubed from 0 to L. Substituting that in, we obtain a center of mass of 3/4 L. Notice how that's different than the centroid, which would be at L over 2. Now, physically, you've felt centers of mass before. It's that particular location where the object would balance. In this case, it's at 3/4 L. Thinking in terms of centers of mass can often help with centroid computations. If you consider a region and break it up into pieces, you can focus all of the areas of those individual pieces at their centroids and weight it according to the area of the piece. Then, by computing the center of mass of this collection of weighted points, you can sometimes make the problem much easier. This even works with negative areas, thinking in terms of a negative mass as well. That can allow you to simplify a lot of computations, as we'll see when we talk about moments.
Centroids and centers of mass are incredibly useful. If you go to the bonus material for this lecture, you'll see how to put centroids to work in computing volumes and forces. We'll continue our exploration of solid bodies in our next lesson with moments of inertia.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 40, Bonus Material. In an earlier lesson on volumes of revolution, we saw an example where the volume seemed to be equal to the area of the cross-sectional shape times what we called the circumference of the center, that is, the distance that the middle of that disk traveled around the axis. Now we have a little bit more expressive language to say what we mean. This is, of course, not the center of the disk, but the centroid. I wonder if that holds in any more generality. Well, indeed it does, and the content of Pappus's theorem states that the volume of an object of rotation is equal to the cross-sectional area times the distance that the centroid travels. So, for example, if we took a more interesting shape and rotated it about a non-intersecting axis, then computing its volume would not be so difficult. Let's look at this specific example where we take an object that is formed by cutting out quarter circles from a square. That is your cross-sectional area, and then rotating that about an axis that is a distance, capital R, away from the middle. Now, computing the centroid of this object is going to be pretty simple, as is computing the area. Let's assume that these quarter circles all have radius little a, and therefore the square that circumscribes them has side length 2a. In this case, by symmetry, we know exactly where the centroid is. It's right in the middle. And so the volume is going to be equal to 2 pi r, that's the distance that the centroid travels about the axis, times this cross-sectional area. What's that? It's the area of the square minus the area of these 4 quarter circles. That's 4 minus pi times a squared. That is much simpler than setting up and solving the associated integrals. What happens if instead of a solid volume, we take a curve and rotate that about an axis? Is there anything we can say about the surface area of that surface of revolution? Well, indeed there is. Pappus's theorem works in this case as well. The surface area is equal to the length of the curve that you're rotating times the distance that its centroid travels. If we look at the specific example of rotating a semicircle of radius r about an axis to obtain a sphere, then we'll see that in this case, as indeed in many cases involving curves in the plane, the centroid is not located on the curve, but rather at a point that is in the plane but not on the curve. In this case, because of symmetry, we know that y bar is equal to 0. But what is x bar? Well, if we knew it, then we could compute the surface area as 2 pi times x bar, that's the distance traveled by the centroid, times L, the length of the curve. Now, it's interesting to note that in this simple example, since we already know the surface area and we know the length of the curve, we could determine x bar in this way. But let's do an example of computing this x bar from the definition. This is the integral of x dl divided by the integral of 1 dl using the arc length element. Of course, since the length is pi times r, we know that denominator. What about the numerator? Well, we have to integrate x dl. dl is somewhat complicated. It's the square root of 1 plus x squared over a quantity r squared minus x squared dx. That does not look like a pleasant integral to do. So let's switch to a different coordinate system. Let's think in terms of polar coordinates. At any particular angle theta, the arc length element is r times d theta. That's going to be a bit easier to work with. In this case, theta is going from negative pi over 2 to pi over 2, and we have to integrate x times dl, that is x times r d theta. Now the r's cancel, and we're left with the integral of x d theta. In polar coordinates, x equals r times cosine theta. And now, that's an integral that we can easily do. I'll leave it to you to check that after dividing by pi out front and evaluating the integral, we get 2r over pi. Let's check that we didn't make any mistakes by plugging that in to Pappus's formula for the surface area. When we do so, we get some cancellation and obtain the familiar result of 4 pi r squared. Now you can imagine how useful this would be in the context of a more interesting looking curve rotated about an axis. Centroids have a habit of cropping up in all sorts of computations. For example, when we looked at the force of a fluid on the end cap of a tank, a cylindrical tank of radius r, then we computed that that force was equal to rho, the weight density, times pi r cubed. Now there's another way to interpret this. In general, for a vertical submerged plate that a fluid is pushing on from the side, the force, the net force, is equal to rho times the area, A, of that plate times x bar. That is the depth from the top of the fluid to the centroid of the plate. Let's check and see that that indeed happened in our example. The centroid of that disk is, of course, right in the middle, and that is a distance of capital R, the radius, from the top. So that, in this case, we would get rho times r, the distance of that centroid, times the area of the disk, pi r squared. Indeed, that matches up with what our more difficult integral computation gave. In general, there are many examples of physical problems where knowing the centroid, or in more generality, the center of mass, is helpful. Keep your eyes open and see if you can recognize some other examples where knowing a centroid will help. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 41 on moments and gyrations.
Centers of mass are wonderfully visceral. You can just feel it when you've balanced something right at its center. There are other properties of solid bodies that integrals help explain. In this lesson, we will consider moments of inertia, a measure of resistance to rotation about an axis.
You may recall from your previous exposure to physics the moment of inertia denoted I. It is a measure of resistance to rotation about an axis. In this, it's not unlike mass, which is a measure of resistance to translation. Thinking of m as the constant of proportionality between force and acceleration allows us to consider moment of inertia, I, as the constant of proportionality between torque and angular acceleration. Let's begin in the case where our object is a point mass. We choose some axis about which to rotate. What does that moment of inertia depend on? Well, it certainly depends on the mass. The heavier the object, the more difficult it is to rotate it. It also depends on the distance, r, to the axis. The longer the distance, the greater moment of inertia. In this setting of a point mass, the moment of inertia is equal to r squared times m. Now, that's the simple case of a mass concentrated at a point. What happens when we have a more interesting object whose mass is distributed over some domain? Well, we're going to think in terms of calculus. What would the appropriate technique be? You won't be surprised to see that the right way to proceed is to divide the object up into differential elements and integrate. If we consider a mass element, dm, as that portion of the object, distance r, to the axis, then the moment of inertia element, di, is given as r squared dm. And so to compute the moment of inertia, we integrate that element, integrating r squared dm. Now, a good physical understanding of moment of inertia is crucial for interpreting our results. Consider a simple experiment where we take 3 round objects whose mass is distributed in different ways and let them roll down an inclined plane. As they roll, they'll be rotating about their axis. The way that the mass is distributed influences the speed at which the gravitational force acts to cause rotation. An object whose mass is all distributed at the outside is going to have much greater moment of inertia than an object whose mass is distributed evenly over the entire disk. Let us compute the moment of inertia in the specific case of a disk, a flat disk of radius r, rotated about, say, the y-axis, centering this in the xy plane. In this case, we need to divide the disk up into elements parallel to the axis of rotation. The inertia element is r squared dm. The mass element is, of course, rho, the density, times the area element, dA. Now, using the fact that our distance to the axis is, in fact, x, we have an integrand of x squared times rho times twice the square root of capital R squared minus x squared dx. When we integrate this to get the moment of inertia, we can simplify things a little bit by integrating from 0 to capital R and then multiplying by 2, taking advantage of symmetry. Even so, this integral looks involved. We're going to need to try, at least, a trigonometric substitution. Substituting x equals capital R sine theta will allow us to clear out that square root and obtain the integral of x squared, that's r squared sine squared theta, times what happens to the square root. That gives us an r cosine theta times dx, which is going to give another r cosine theta. The resulting integral has even powers of sine and cosine and would take a little bit of thinking in order to work through. Instead of doing that explicitly, let me claim that the answer is not so bad. It works out to 1/4 rho times pi times capital R to the 4th. We can simplify that a little bit, taking advantage of the fact that the mass is pi times r squared times rho. That gives us a moment of inertia of 1/4 m r squared. Well, to prove that result that we didn't justify, let's change perspectives a little bit and compute the moment of inertia when this disk is rotated about the center, about the z-axis, if you will. In this case, we need to divide into area elements parallel to or at a fixed distance from the axis of rotation. Let's call that radial coordinate r. Then the inertia element is r squared times rho times the area element, in this case 2 pi r dr. Now this integral is not going to be so bad. We have to integrate r cubed dr as r goes from 0 to capital R. That, of course, gives us an answer of pi rho over 2 times capital R to the 4th. Substituting in the mass, we obtain 1/2 m r squared. That was much simpler, but not unrelated to the problem of rotating about a vertical axis. Think of it this way. The moment of inertia is the integral of r squared dm. In the xy plane, as we have set things up, r squared is equal to x squared plus y squared. If we distribute that integral over addition and consider each piece, well, we recognize something. The integral of x squared dm really gave us the moment of inertia of that disk rotated about the vertical axis. What would the integral of y squared dm give us? Well, you shouldn't be surprised to see that that's really the moment of inertia rotated about a horizontal axis. But because this is a symmetric domain, these two are of course equal to one another. Therefore, we have, given the fact that the moment of inertia about the center is 1/2 mr squared, we can conclude that the moment of inertia about the vertical or horizontal axis is half of that, as we saw in our previous slide. Let's consider a different, simpler sort of object, a rectangle, let's say of length L and height h. We're going to rotate that about a vertical or a horizontal axis. Which do you think would have the greater moment of inertia? Well, let's compute both and find out. In this case, we need to compute the integral of r squared rho dA, whereas before, rho is the density. In the case of rotation about a vertical axis, our area element is that obtained at some distance x to the y-axis, and it is a vertical strip. We need to integrate r squared rho dA, that is x squared times rho times h dx. The limits are x goes from negative L over 2 to L over 2. That's a simple integral. X squared integrates to x cubed over 3. And evaluating at the limits, we get 1/12 rho HL cubed. It's sensible to substitute in the mass. That is rho times L times h, yielding an inertia of 1/12 mL squared. I'm going to leave it to you to do the same in the case of rotation about a horizontal axis, where we wind up following the exact same procedure, but exchanging L for h, and vice versa. This yields an inertia of 1/12 mh squared. We're going to take a moment and consider a related physical concept, that of the radius of gyration. The radius of gyration is the answer to the question, if all of the mass of the object were focused at a single point, how far from the axis would it need to be in order to give the same moment of inertia? Now, you've felt the radius of gyration before. If you've ever hit an object with a bat, if you get it at just the right spot, it feels right. That is the radius of gyration. We denote it capital R sub g, and it satisfies the equation that I equals m, the entire mass, times r sub g squared. Taking that equation and solving for r sub g, we obtain a formula, the square root of I over m. That's simple enough, but think about what we're doing. I is really the integral of little r squared dm. M is really the integral of 1 dm. And so in this ratio, we're really looking at the average of little r squared. Taking the square root of that gives us the root mean square of the distance, little r, to the axis. That is really what this radius of gyration means. It's a root mean square of distance to the axis. Now, it's perhaps worth taking a moment or two and thinking about what this radius of gyration means and what different examples have. If you look at a tennis racket or various kinds of sports objects, in fact, if you go through your house and just pull out random items that you have lying around, you can physically measure the radius of gyration and start to get a feel for how different objects have their masses distributed in different ways. This entire lesson concerns the question of how mass is distributed over an object. If we consider a slightly simpler setting where the object is one-dimensional, we split it up into mass elements based on this coordinate x. Then, for irregular shaped objects, the mass might be concentrated at different places. The moment of inertia is one way to get at that. Integrating x squared dm leads us to the moment of inertia, or after normalizing and taking a square root, the radius of gyration. These are both measures or ways to characterize how the mass is distributed. Sometimes an integral of this form is called the second mass moment. Well, anything that has the name second mass moment would lead you to wonder, what is the first mass moment? It is, as you might guess, not the integral of x squared dm, but the integral of x dm. This, too, tells you something about how mass is distributed across the object, but in this case, it leads to the centroid when properly normalized. And so, both of these integrals are giving you different physical properties about how mass is distributed. There are other moments as well, all of which answer that same question. The higher mass moments are integrals of the form x to the n dm. And you may well wonder, what sorts of physical properties do these integrals give? Well, we're not going to have time to answer that now, but I will say that there is one more mass moment that you know. That is the zeroth mass moment, or the integral of x to the 0 dm. That, of course, is just the integral of dm, which is m, the mass.
This concludes our treatment of solid bodies through integrals, of masses, middles, and moments. In our next lesson, we'll start learning about probabilities. It won't be as discontinuous a jump as you might think, so stay tuned.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 41, Bonus Material. One of the properties of moments of inertia that you're going to find very helpful when doing problems is that of additivity. This comes from the fact that moments are integrals, and you can break them up into pieces. For concreteness, let's consider an example, a simple H shape with the dimensions being given as shown in terms of constants A and B. Now, compare what the moment of inertia of that shape is going to be to the same shape rotated by 90 degrees. Let's consider a horizontal axis that passes through the center of each shape, an H shape and an I shape. Well, let's begin with the H. What is the moment of inertia? We can decompose this shape or region into rectangles, and we know the moment of inertia of a rectangle about a horizontal axis by computing the dimensions of this rectangle. The height is going to be A. The width is going to be A minus B over 2. Then we can get the moment of inertia of this rectangle as 1/12 A cubed times A minus B over 2. Now, of course, there's a corresponding rectangle on the right. That is going to have the same moment of inertia. We add it to what we computed before. And then we have one more term to add, the small square in the middle, of dimensions b by b. That contributes 1/12 b cubed times b. When we add all of these together and do a little bit of algebraic simplification, we obtain a moment of inertia of 1/12 quantity a to the fourth plus b to the fourth minus a cubed b. Now, on the right, we can't do exactly the same thing with rectangles about that axis. But look what we can do. We can compute the moment of inertia of the outer square that bounds this I. That's 1/12 a cubed times a. And then we can subtract off the moments of inertia of the holes that we would cut through on the left and on the right. And again, we know the dimensions of these rectangles to be b in height and a minus b over 2 in width. When we combine these terms, we obtain a moment of inertia that is similar in form but slightly different. I is equal to 1/12 a to the fourth plus b to the fourth minus ab cubed. Now, how might this be useful? Well, remember, we once talked about the differential equation associated with the deflection of a beam. And one of the coefficients in that equation was I, the moment of inertia of the cross-section of the beam about a horizontal axis. Now, if you had two different choices for your beams, an H-beam or an I-beam, well, which one is best? Perhaps you should look around you and see which choices get used in practice. But from our computation, we can see which one has the more preferable moment of inertia, because these two terms differ only at the very end. Minus a cubed b for the H-beam and minus ab cubed for the I-beam. We know that a is bigger than b. There is one more result that is going to be extremely helpful in doing computations. This is called the parallel axis theorem. We begin with the domain and consider the moment of inertia about an axis that passes through the center of mass. This moment, I naught, is the integral of r squared dm, where r is the distance to this center axis. Now consider what happens when you choose an axis that is parallel to this center of mass axis, but some distance d away. What is the moment of inertia about this axis? Well, it's clear that it's more, but by how much? Well, if we compute this moment, call it I sub d, this is the integral of the distance to this axis squared, dm. What is that distance? Well, we could write this as r plus d, where r is again the distance from the center of mass axis. Now, let's take that integrand and expand it out. What do we get? We get 3 integrals with respect to dm. The first is the integral of r squared dm. That is, of course, our moment of inertia about the center of mass. What about that second term? We're integrating r dm. Now, remember our definition of the center of mass. This is precisely where that comes from. And in our coordinate system, the center of mass has r value equal to 0. Therefore, this second integral vanishes. R balances because we're passing through that center of mass. The last term is simply the constant d squared times the integral of dm. The integral of dm is m, and so we obtain that I sub d is I naught plus d squared m. This is the content of the parallel axis theorem and allows for a simple computation of some moments. For example, let's consider the moment of a flat round disk of radius capital R about an axis located some distance d away from the center. What would that be? Well, we know the moment of inertia passing through the center of the disk, that's 1/4 mr squared. By the parallel axis theorem, the moment of inertia about this parallel axis, a distance d away, is 1/4 mr squared plus md squared. You could find this result useful in many different contexts. For example, you could go back to the I-beam result and compute the moment of inertia based on translated rectangles. I'll leave it to you to practice through some of the homework problems and see where you might make use of the parallel axis theorem and of additivity. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 42, Unfair Probability.
Let's take what we've learned about averages, moments, centroids, and put them to use in an entirely different setting, that of probability. We're going to begin our introduction to probability with a geometric treatment that is both visual and visceral.
All probability begins with counting. Consider something as simple as asking what happens when you roll a pair of dice. What's the probability that the sum of the numbers you get adds to greater than 7? Well, in this case, you can simply make a table with all of the possible outcomes for the first and the second die, add up their face values, and identify which of those are greater than 7. When you do so, the probability is a ratio of the number of outcomes that are greater than 7 to the total number of outcomes. In this case, the numbers work out to 15 over 36. That means you have a little bit less than a 50-50 chance of getting something bigger than 7. Now this is simple enough, but do you see an integral hiding in here somewhere? Stay tuned. Consider a simple situation of spinning a dial. Some outcomes you win, others you lose. You could compute the probability of a win by counting sectors as before, but there's another way to approach this. One can think of the random variable as being an angle where some angles connote a win. Spinning the dial corresponds to choosing an angle at random between 0 and 2 pi. In this case, how would you compute the probability? Well, one could think of it as a ratio between the number of winning angles to the total number of angles. But we're really not counting angles, are we? We're really computing length. In this simple example, one would get an answer that is the same as counting segments. But in other examples, we would really need to compute lengths. For example, what's the probability that a randomly chosen angle on the circle has sine larger than 1/2? Well, we would compute this probability as a ratio, as before. The total number of angles has length 2 pi, the length of the circle. If we look at those angles that have sine larger than 1/2, well, that length is 2 pi over 3. Taking the ratio gives us a probability of 1/3. We can do the same thing with area. With what probability does a randomly chosen point in a square lie within the inscribed circle? So take a square, consider the inscribed circle, and then choose a point in the square at random. Think of it as throwing a dart. What are the odds that you land inside that circular region? Well, in this case, it's going to be an area fraction. We would take the area of the disk and divide by the area of the square. That is our probability. We can compute that easily enough. If the radius is r, then the disk has area pi r squared, and the square has area 2r quantity squared. That leads to pi over 4, or about 79%. Those are your odds. In some contexts, volume is the appropriate tool. Consider the following. With what probability does a randomly chosen point in a ball lie within the outer 1%, that is, within 1% of the boundary, as measured by radius? So we have a solid ball, radius r. It's the point that is chosen at random, not the radius. Given a random point in that ball, what are the odds that its radial coordinate is within the outer 1%? Well, we have to think in terms of volumes, since this is a three-dimensional ball. We know the volume of a ball of radius r is 4/3 pi r cubed. So, to compute the probability in this case, what kind of computation should we do? Well, given our formula for volume, it's really easy to compute the volume of a ball. If we pick a point at random in the ball, then the total volume of the possibilities is 4/3 pi r cubed. Now, what are the odds that a randomly chosen point lies within the inner 99%? Well, that too is a ball of radius 0.99r. And so if we look at this fraction, this ratio of volumes, this gives us the odds of not being within the outer 1%. So to compute the odds of being in the outer 1%, we take 1 minus this ratio. What you'll notice is that there's some convenient cancellation that goes on. The 4/3 pi cancels, and the r cubes cancel, and we're left with 1 minus 0.99 cubed. That works out to about 0.0297, etc. That means there's about a 3% probability of being within that crust, that outer shell. Notice it's not 1% because it's the point that is random and not the radius. Now, having done length, area, volume, of course, you know what's coming next. That is high-dimensional volume or hypervolume. In this case, let's repeat the problem with a ball of dimension n. In this case, the volume of an n-dimensional ball of radius r is some constant v sub n times r to the n. You don't have to remember what that constant v sub n is, because if we follow the exact same steps as before, computing the probability of being within that outer 1%, we get the ratio of the volume of that inner 99% ball, which is v sub n times 0.99r to the nth, divided by the volume of the full n-dimensional ball, v sub n r to the n. Just as before, the v sub n's cancel, the r to the n's cancel, and we are left with 1 minus 0.99 to the n. Now, what happens as n gets large? 0.99 to the n goes to 0, and we're left with the somewhat surprising conclusion that when the dimension is high enough, for example, if it is 459 or bigger, then 99% of the volume of this ball is in the crust. If you pick a point in the ball at random, your odds of being within 1% of the boundary are greater than 99%. That comes as a bit of a surprise, but not if you know how high-dimensional volume works. These examples illustrate the basis of what we call fair probability or uniform probability. For a uniform probability distribution over some domain, D, whether it's a ball or a circle or a square, then the probability of a random point being in some subset, A, within D, is given by a fraction, by a volume fraction. The probability of being within A is the ratio of the volume of A to the volume of D. In this case, what we mean by volume is dependent on the dimension. When we were spinning a dial, we looked at length. When we were choosing a point at random in the square, then we considered area fractions. When we were choosing a point on a ball, then we were considering volume, either three-dimensional or higher dimensional, depending on the dimension of D. And lastly, when we simply rolled dice, we were counting, but that counting is in itself zero-dimensional volume, the volume associated to a discrete set. Now that one example had some unique features in that there were two variables, the two die, and they were independent, and so we could compute probabilities in terms of multiplication. For an example that involves both independent variables and integrals, we're going to consider the classical Buffon needle problem. This problem goes as follows. Consider a collection of parallel lines in the plane, separated by some distance L. Then drop a needle on the plane. Let's say the needle also has length L. Then, what are the odds that you have a crossing, that the needle crosses one of the lines? Well, one way to answer this question would be to drop a whole bunch of needles, count how many of them cross the line, and divide by the total number of needles that you dropped. That would be an approximation, but we can do better than that. If, as stated, we let L denote the distance between these parallel lines and the length of the needle, then what variables do we use to characterize where a randomly tossed needle has fallen? We'll let H denote the horizontal distance from the leftmost tip of the needle to the rightmost nearest line. But that doesn't completely characterize the needle. We also need to know theta, that is the angle that the needle makes with this line. Now, what are the bounds on H and theta? H can vary between 0 and L. Theta doesn't vary from 0 to 2 pi, but rather from 0 to pi by means of how we've defined H in terms of the left tip. Now, given this, how can we say whether or not a needle crosses a line? Well, if we set up a right triangle based on that needle, then the hypotenuse is of length L, and we know the angle theta. Therefore, the horizontal width of this triangle is equal to L times sine theta. If that quantity is greater than or equal to H, then we have a crossing of the line. So, if in this theta H plane we graph L times sine theta, then dropping a collection of needles is the same thing as sampling this rectangle at random. And any random point that obeys this inequality, that falls under the curve, connotes a crossing. And now we can do some calculus. Because these variables are independent. Changing h doesn't change theta, and changing theta doesn't change h. Then we can compute the probability of a crossing as an area fraction. In this case, taking the ratio of the area under the curve to the total area of the rectangle. What's the area under the curve? Why, that's simply the integral, as theta goes from 0 to pi of L sine theta d theta. What's the area of the entire domain? It's the area of the rectangle, pi times L. Now I think that you can do this integral in your head. Noticing that the L's cancel, one obtains a probability of 2 over pi. That's very interesting, but maybe more interesting than you might suspect because of the following fact. This probability has pi within it, and we have an interpretation in terms of dropping needles on, say, a sheet of paper. This, in principle, means that you should be able to approximate the value of pi simply by dropping needles on a field of lines, counting how many times the needle crosses the line, and then dividing by the total number of needles that you dropped. That ratio should come closer and closer to 2 over pi. By taking the reciprocal, multiplying by 2, you can, in principle, approximate pi. Maybe you should try it. If you do, one of the things that you'll find is that probability is a somewhat mysterious subject. You'll also learn a thing or two about convergence.
Our treatment of probability won't end with volumes and needles and pi. In fact, we've hardly begun. In our next lesson, we're going to consider what happens when the world isn't fair, or at least when the underlying probability distribution isn't fair. To do that, we'll need to wed our volumetric approach with a more mass-based approach from our previous lessons.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 43 on probability densities.
We've seen that fair or uniform probabilities lead to geometry, to counting, length, area, and volume. But what happens when probability is not fair? In this lesson, we'll define and describe probability density functions.
In our last lesson, we computed probabilities under the assumption of fairness, namely that any point is as likely as any other point to be chosen at random. This is not always a good assumption. There are many instances where there's a bias, where certain outcomes are more likely than others. This bias is encoded in the notion of a probability density function, sometimes called a PDF. This is a function over a domain that tells you what outcomes are more likely than others, such as exam scores or heights. We define a probability density function, rho, as a function that satisfies the following two criteria. First, rho is non-negative, and second, the integral of rho is equal to 1. We have to specify a little bit more, namely a domain D on which we are discussing the PDF. So, in particular, the integral of rho over D equals 1. Now that's the definition, but it's certainly not a very intuitive definition. What does it mean? Before answering that, let's consider a specific example in the context of a collection of light bulbs. These light bulbs will eventually fail, but the question is, when? It happens with some sort of randomness. But how is this randomness regulated? Well, there's some underlying probability density function. Let's assume that it were exponential. That is, the light bulb is more likely to fail early and less likely to fail later on. This would be a function, rho of t, of the form e to the minus alpha t, let's say, where t is time and alpha is some positive constant. Is this a PDF? Well, it is certainly satisfying the first criterion. It is non-negative. As for the second criterion, let's specify a domain, d, for the time, as 0 to infinity. Then, in this case, what would the integral over this domain be? Well, integrating an exponential function is easy enough. This gives e to the minus alpha t times negative 1 over alpha. Evaluating from t to infinity, we get 1 over alpha. This is not going to work unless, of course, alpha is equal to 1. So, what we could do is modify the PDF by adding a coefficient of alpha out in front. If we do that, then the integral is going to be equal to 1. Now, that's a good example of a PDF, but we still don't know quite what it means. Well, let's consider that meaning in the context of fairness, which we already have some experience with. Fairness connotes a uniform density function. That means a PDF that is constant on the domain. What would that constant be? Well, it has to satisfy the integral over d equals rho, that is this constant, times the volume of the domain. Now, in order to be a PDF, this has to satisfy that integral equals 1. So what does that tell us about rho? Rho, this constant, must be 1 over the volume of the domain. Let's see what that looks like in the context of the domain being an interval, let's say from A to B. In this case, rho is 1 over the length of this interval. That is 1 over B minus A. What would it look like in the case of a discrete or zero-dimensional domain? Well, let's say we had a die, a single die. Then the domain consists of 6 points, the different outcomes for the faces. The PDF would be 1 over the volume of this domain. Volume in dimension 0 being simply counting. This means that rho is equal to the constant 1/6. If we had a different discrete set, let's say for flipping a coin, then since we only have 2 points in that domain, heads and tails, then rho would be equal to 1 over 2, or 1/2. Now consider this more carefully, because what we have in general is that for a discrete set of n points, rho, a uniform density, is the constant 1 over n. In the case of, say, flipping a coin, notice that the value of rho is precisely the probability of getting that outcome. You have a 50-50 chance for getting heads. If you roll a 6-sided die, your probability of landing on any one outcome is 1/6. Notice also what happens if you want to consider the probability of landing in a collection of outcomes. Let's say, what's the probability of getting 4 or 5? Well, we would add up these values of rho. 1/6 plus 1/6 is 1/3. Now, does that intuition carry over into the continuous case? No. The probability of landing at any single point in an interval is not 1 over the length of that interval. Not at all. However, if we take a subinterval, then we can make sense of the probability in terms of lengths. If we consider with what probability does a randomly chosen point in a domain D lie within a subset A of D, then we have answered this question in the case of a uniform probability density function. We know that the probability of landing in A is the volume fraction. That is, the volume of A divided by the volume of D. We could write that as the integral over the domain A of 1 over the volume of D. But that is precisely the integral of the uniform PDF rho, that constant 1 over volume of D, but integrated over A, not over all of D. This leads us to consider more generally the formula that the probability, capital P, of landing in A with a point chosen at random is the ratio of the integral of rho over A to the integral of rho over D. And this explains why we want the integral of the PDF rho over all of D to be equal to 1, so that we can simply write the probability of landing in A as the integral of the PDF over the subdomain A. This holds in the uniform case, but it also holds in general. If we have a non-constant PDF and we want to know what is the probability of lying or landing in a subset A, we integrate the probability element, that is, rho of x dx, over the domain A. Let us interpret these results in the simple case of a domain being the interval from A to B. Given our PDF rho, what is the probability that a randomly chosen point in that domain lies between A and B? Well, by our definition, this probability P is the integral of rho of x dx as x goes from A to B. Well, that integral is, by definition, 1. What does that mean? When you see a probability of 1, that means yes, it will happen. But let's keep going. What's the probability that a randomly chosen point is exactly A? Well, that probability is the integral of rho of x dx as x goes from A to A. From what we know about integrals, that is equal to 0. When you have a probability of 0, this means no, it's not going to happen. What's the probability that a randomly chosen point is closer to A than to B? Well, we would simply integrate rho of x dx from the left point A to the midpoint of the domain. For concreteness, consider the example of a company that advertises half of its customers are served within 5 minutes. What are your odds of having to wait for more than 10? Let's assume an exponential PDF rho of t is alpha e to the minus alpha t over the domain from 0 to infinity. Our first problem is we don't know alpha, but we do know the probability of your serving time being in the interval from 0 to 5. That is, by definition, the integral of alpha e to the minus alpha t dt as t goes from 0 to 5. And we're told that that probability is 1/2. Now, we can do that integral easily enough, evaluating at the limits, and then doing a little bit of algebra to solve for alpha. I'm going to leave it to you to follow the computations and see that alpha is 1/5 times log of 2. With that in hand, we can now address the question of the probability of having to wait for more than 10 minutes. Now, we would compute the probability of being in the interval from 10 to infinity. Thus, we would perform the same integral as before, but evaluated at limits. T goes from 10 to infinity. This yields e to the negative 10 alpha. If alpha is 1/5 log 2, what is negative 10 alpha? It's negative 2 times log of 2. That is log of 2 to the negative 2 power. When we exponentiate that, we get 1 over 2 squared, or 1/4. That means that you have a 25% chance of having to wait for more than 10 minutes. That doesn't sound so good. But what are the odds of having to wait for more than 30 minutes? Well, we would follow the same computation and need to compute negative 30 alpha. That is log of 2 to the negative 6th. Substituting that in would give us odds of about 1.5%. There's one type of PDF that is of crucial importance that you're going to see again and again. This is called a Gaussian, or sometimes a normal PDF. This is the function rho of x equals 1 over the square root of 2 pi times e to the minus x squared. You've probably seen this before. This is sometimes called a bell curve. It has a peak around x equals 0 and then drops off. Now, there are a few things to observe. First of all, in this case, your domain is the entire real line. That is, this is a setting of infinite extent. Anything could happen. Your PDF is certainly positive. In fact, it's strictly positive. But the tricky thing is in verifying that it's a PDF. That is, in verifying that the integral over the entire real line is equal to 1. You're going to have to trust me on that for now. You don't quite have enough at your disposal to prove this. Now, you will often see Gaussians that are translated about some middle point or mean. You'll often see them stretched out or rescaled somehow. What I want you to know about Gaussians for the moment is that they are everywhere and all about. Gaussians come up in somewhat surprising places. If you look at the binomial coefficients that you obtain from Pascal's triangle and consider what the rows look like, you notice that the rows tend to go up in the middle and then down at the sides in a manner reminiscent of a shifted Gaussian. In fact, if you were to divide these binomial coefficients by 2 to the n, where n is the row number, then you'd obtain something that in the limit, as you go down, converges to something very much like a Gaussian. This is a hint at one of the deeper truths of mathematics, that Gaussians are limits of individual decisions, left or right, heads or tails, that compound upon one another to converge to such distributions. Gaussians are indeed everywhere.
So now we see not only what a probability density is, but also how to compute a probability by means of integration. In our next lesson, we'll introduce a few of the main characters of probability theory and see what role they have to play in our story of calculus.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 44 on expectation and variance.
Do you think that it's a coincidence that we use the term probability density function? By no means. In this lesson, we'll explore the analogy between masses and probabilities, and we'll consider some standard concepts from statistics, that of expectation, variance, and standard deviation.
Let's say that you are given a probability density function, rho of x, over the reals. What might you be able to say about a point chosen at random with respect to that density? Well, you might want to know, what outcome is most likely? What do I expect to see on average? On the other hand, since obtaining any particular value is very, very unlikely, you might want some way to quantify your uncertainty of that expected value. These ways of characterizing a PDF are the focus of this lecture. We begin with two standard definitions from probability: the expectation and the variance. The expectation is also called the mean, or the expected value, or the first moment, and it is defined as E equals the integral over the domain of x dp. In the one-dimensional setting, this is the integral of x times rho of x dx. The expectation is telling you something about the most likely value, or the average value. Now, it may occur at the peak of the probability density function, or it may not. It depends on how that density is distributed over the domain. The variance is sometimes called the second central moment. It is denoted V, and it is defined as the integral over the domain of quantity x minus e squared dp. We can interpret x minus e as a distance from the mean. And so in the one-dimensional case, we can write this as quantity x minus e squared rho of x dx. What happens when we expand out that multiplication and split this into three integrals? We get some very nice simplifications. Notice that the middle integral and the last integral are things we've seen before. The middle integral, that of x dp, gives the expectation. The final integral, the integral of dp over the domain, is, of course, 1. Thus, we can simplify the formula for the variance to the integral over the domain of x squared dp minus the expectation squared. That is an important formula, and you're going to want to remember it. Maybe you've seen something like it before. It will help us understand just how to visualize or interpret this variation. By now, you've probably noticed that there's a relationship between what we've done in probability and what we've done in mass. If we consider a probability density function, rho, over a domain, let's say an interval from A to B, you've noticed that we've used the same symbol, rho, for the PDF and for a mass density in a more physical context. Indeed, the mass element, rho of x dx, is precisely what we use as the probability element. In that case, what is the mass? Well, it's the integral of the mass element. That corresponds to the probability, p. Now, let's consider the expectation that we have just defined, e. What is that? That's the integral of x dp. Now, of course, by the definition of a PDF, this is really the same thing as the integral of x dp over the integral of 1 dp. And so what we're really doing is computing the average x value with respect to the probability measure. That is something that we have seen before in the mass context. That is the centroid x bar. So you can think of the expectation as a probabilistic centroid. Well, if that's the case, then how do we interpret the variance? That is, the integral of x minus e quantity squared, dp. Well, you no doubt recognize that that is the moment of inertia, but rather the moment of inertia about the centroid. Now that's a very nice physical interpretation. That means we can think of the variance as something like a measure of resistance to rotating the domain about its mean. If that's the case, then what is the probabilistic interpretation of the radius of gyration, that distance at which one could focus all of the mass and have the same inertia? Well, that is a well-known object in probability called the standard deviation. Denoted by sigma, it is defined to be the square root of the variance, and it is a measure of how the mass, if you will, is distributed about the centroid. It's a measure of the spread of the variance about the expectation. Now, with this in hand, let's compute some of these values. In the case of a simple PDF, let's look at a uniform density over the interval from a to b. What's the expectation? Well, it's the integral of x dp. That is, the integral of x times rho of x dx, as x goes from a to b. Rho of x, being simply 1 over the length, b minus a, gives us a very simple integral. When we evaluate it and do a little bit of algebra, you won't be surprised to find that the expectation is 1/2 a plus b. The average value is right in the middle of the domain. What's the variance in this case? Well, we have to integrate quantity x minus e squared times rho of x dx. Using the formula that we derived a little bit ago, we can take advantage of the fact that we already know the expectation. And so we're reduced to integrating x squared dx. That much is simple enough, but you'll find when you go to do this that there's a little bit of algebra that's involved in order to simplify. I claim that with a little bit of work, one gets a variance of 1/12 quantity b minus a squared. Now, how do I know that I haven't made a mistake here? According to our physical interpretation, this variance should be related to the moment of inertia of a region about a centroid axis. Recall that for a rectangle, we have the moment of inertia as 1/12 m, the mass, times L squared. In the probabilistic context, the mass is 1, and this length is b minus a. So I'm confident that we got this one right. The standard deviation is the square root of the variance. That is the square root of 1/12 quantity b minus a squared. In other words, b minus a over 2 root 3. How about a different density function, an exponential density over the domain from 0 to infinity? Well, the expected value is the integral of x dp. In this case, with an exponential density, we have to integrate x times alpha e to the minus alpha x dx, as x goes from 0 to infinity. This is going to take a little bit of work, but not too much. Using integration by parts, we get minus x times e to the minus alpha x from 0 to infinity plus the integral from 0 to infinity of e to the minus alpha x dx. The former term vanishes upon substitution, and we're left with an easy enough integral. We obtain negative 1 over alpha e to the minus alpha x from 0 to infinity. Evaluating, we obtain 1 over alpha. Now that's a very, very simple expectation. You're probably going to want to remember this, since exponential density functions are fairly common. The variance in this case is going to be a bit more work. We're going to have to integrate x squared dp and then subtract off the expectation squared. This integral is going to, again, involve integration by parts, but we're going to have to do it twice since there is an x squared in front of the exponential term. I hope you'll trust me when I claim that this variance reduces to 1 over alpha squared. This means that the standard deviation is equal to 1 over alpha. Let's put this to use in a simple example. Let's say that a light bulb is advertised as having an average lifespan of 2,000 hours. What are the odds that your light bulb fails within 400 hours of use? You might think, well, that's very unlikely since they say the average lifespan is 2,000 hours. But let's see. If we assume a probability density function that is exponential and of the form alpha e to the minus alpha t, where t is time, then what could we say about alpha? Well, knowing that the expected value is 2,000 hours, and knowing that that expectation is 1 over alpha for an exponential PDF, what can we say? Well, we know that alpha is 1 over 2,000. And to compute the probability of failure within 400 hours, we want the probability of landing in the interval from 0 to 400. That is simply the integral of alpha e to the minus alpha t dt as t goes from 0 to 400. Now that integral is easy enough. It yields minus e to the minus alpha t. Evaluating from 0 to 400, we obtain 1 minus e to the minus 1/5 because negative alpha times 400 is minus 1/5. Now, that evaluates to about 0.18, meaning that there's nearly a 1 in 5 chance of a failure within the first 400 hours. Recall from our previous lesson the ubiquity of Gaussian or normal densities and their form, which looks bad, but is not so much. Note that this is an even function in x, so that the expectation is 0. One of the reasons for the coefficient out in front is so that the variance and the standard deviation will both be 1. Now, this formula for a Gaussian is not the most general possible. There is a general Gaussian of the form 1 over sigma square root of 2 pi times e to the minus quantity x minus mu squared over 2 sigma squared. This general Gaussian allows you to tune the mean and the standard deviation. The expectation is mu. The variance is precisely sigma squared. One of the reasons for using general Gaussians is that many random variables are normal. They have a Gaussian density. If you look at the size of objects, such as people or snowflakes, they tend to be distributed according to a Gaussian. This is often used in statistics. Now, Gaussians can be hard to work with, given their form, but one can keep in mind a few properties. If you have a Gaussian with expectation mu and standard deviation sigma, then you're likely to be within 1 standard deviation of the mean. 68% of the mass of that density function lies within distance sigma. If you are within 2 standard deviations, then the amount of mass goes up to about 95%, and almost all of the mass, more than 99%, lies within a distance of 3 standard deviations of the expectation. Keeping these figures in mind might help you if you ever take a statistics class. Note, however, that there's much more to statistics and to probability than simply remembering a couple of numbers and the general shape of a Gaussian. It's a large and beautiful subject that you'll be able to handle with your knowledge of calculus.
And so we come to the end of Chapter 4. It's worth taking a moment to reflect on all the applications that we've covered, from simple area under a curve all the way up through probability. In our next and last chapter, we're going to tie the entire course together by reconsidering what calculus means in the context of discrete functions.